Pro, please, sir. Professor Khamsi, please. Honorable Vice Chancellor, Professor Naima Khatoon, the Chief Patron of GIAN program, respected Dean Faculty of Science, the patron of this program, Chairman, Department of Mathematics, Professor Shahid Ali, esteemed guest of honor, Professor Mohamed Imdad, the distinguished mathematician and the chief guest of the program, Professor Mohamed Amine Khamsi, the course coordinator, Dr. Javid Ali, the local coordinator of the GIAN program, Professor Bibha Sharma, respected teachers, research scholars, and my dear students, I, Dr. Musawwir Ali, on behalf of Department of Mathematics, extend a warm welcome to each one of you for this inaugural ceremony of GIAN program on fixed point problem, the new and old. As we are the true followers of our cultural values and traditions, so according to the traditions of Aligarh Muslim University, we begin with the academic programs or any gathering with the recitation of holy verses of the Quran. For that, I invite a school student, Zaid Maqsood, please come and recite few verses of the Quran, please. Maqsood.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم قل أعوذ برب الناس ملك الناس إله الناس من شر الوسواس الخناس الذي يوسوس في صدور الناس من الجنة والناس صدق الله العلي العظيم.
Thank you, Zaid. Now it's time to honor our esteemed dignitaries present on the dais to show a gesture of appreciation and respect. For that, I first invite Chairman Saab to present a bouquet to the Honorable Vice Chancellor, ma'am. Sir. Sir. Yes. Thank you. Dr. Javid Ali, kindly present a bouquet to the Dean Faculty of Science, Professor Sartaj Tabassum, sir. May I request the Vice Chancellor to welcome our Chief Guest, Professor Mohamed Amine Khamsi, by presenting him a bouquet. Thank you. Thank you, ma'am. Now I request Professor Kalim Raza Kazmi to present a bouquet to our esteemed guest of honor, Professor Mohamed Imdad. Right. I request Professor Asma Ali to present a bouquet to the chairman of the department. I request, thank you, sir. I request Dean Faculty of Science to present the bouquet to the local coordinator, Professor Bibha Sharma. Sir. Thank you. Lastly, I invite Dr. Aslam Siddiqui to present the bouquet to the course coordinator, Dr. Javid Ali. Because Madam Vice Chancellor has consecutive meetings today, so without any further delay, I request Chairman Saab to kindly deliver his welcome speech. Please.
Professor Naima Khatun, Vice Chancellor, Aligarh Muslim University, Aligarh. The Professor Amine Khamsi, the learned professor at the University of Texas, U.S.A. Professor Sardar Tabassum, Dean Faculty of Science. Professor Bibha Sharma, the University local coordinator of this GIAN program. Professor Imdad, guest of honor and a retired teacher of our department. Dr. Javid Ali, I, on behalf of the department, welcome you all and the participants of this program. I welcome you all to the conference. The fixed point problem, the old and the new, under this GIAN program, which is in fact a program run by the government of India and which aim is to interact the foreign faculties with the universities to uplift and the upliftment of the science and technology. Now, since the program is run by the government of India and local coordinator is here, so more about this program will be illustrated by this local our local coordinator Bibha Sharma and the Professor Dr. Javid Ali will elucidate the on this fixed point problem, the old and the new. I will confine myself just to brief the brief history of our department of mathematics. So actually, when this AMU college was established in 1878 on January 8, the necessity of mathematics was the necessity of the mathematics discipline was strengthened, and when the Mohamed and College was established on January 8, 1877 at Aligarh, mathematics was recognized as an important discipline of the study here, and consequently the necessity of appointing a professor in the subject was strongly felt. So the college was established, and with the establishment of this college, this mathematics discipline was initiated in the college. So by 1910, the college was established in 1878. In 1910, the college had a unique distinction of having its three professors, namely Professor J.C. Chakravarti, Dr. Ziauddin Ahmad, and Dr. M.A. Aziz, and one assistant professor, Mr. Abdul Majid Qureshi, in May 1910. So, as I have already just mentioned, that one of the earliest mathematician associated with the college was Dr. Sir Ziauddin Ahmad, who along with Dr. C. Chakravarti and M.A. Qureshi founded the group of mathematicians and teachers and research workers whose main interests were in astronomy, history of mathematics, and the theory of functions. They carried out many innovations in teaching, and research. And then they formed a society which they call the AMU College Mathematics Society, with its president Dr. Sir Ziauddin Ahmed and its secretary M.A. Qureshi. Mr. M.A. Qureshi was its secretary. The society has been continuing its activities and is now presently is known as Aligarh Mathematical Society. The Department of Mathematics came into existence on the elevation of this Mohammedan Anglo-Oriental College to the status of a residential university in 1920. Thus, Department of Mathematics is as old as this university. So, after the establishment of the department in 1920, Professor André Weil, a French mathematician, joined the department and headed the department for 2 years during 1931 and 1932. Now, our pride, that is the pride of our department, is our seminar library. And because we claim that it is the most valuable mathematics library in any university of the country. During the years which span over a century, the department has acquired more than 22,000 books of higher mathematics. And this number of 22,000 books does not include the books of undergraduate level. Actually, these undergraduate levels books, they are available in our central library, which is known as Maulana Azad Library. The seminar library also contains 50 valuable collected works of eminent mathematicians. Apart from steadily acquiring recent books on advanced mathematics, it also receives more than 150 periodical through subscription and mutual exchange. And moreover, the department has also been publishing a journal known as Aligarh Bulletin of Mathematics since 1971. The bulletin publishes regularly research articles by mathematicians from India and abroad, and Professor M.A. Kazim was its founder, chief editor. Now, in recognition of its inherent potential, the department was recognized as the UGC Department of Assistant Assistants in September 1983, which continued up to March 2003. And the discipline of algebra, analysis, and differential geometry were recognized as the thrust areas of mathematics. The department was further strengthened by the award of UGC COSIST program in March 1994. The National Board of Higher Mathematics has also provided financial support in the form of annual grant for acquiring books and journals of our department. The successful completion of DRS Phase 1, which starts from April 2071 to March 2012, the department led to its extension to DRS Phase 2, starting from April 2013 to March 2018, for the upliftment of teaching and research under thrust areas, and subsequently the department was also selected for DST FIST program during 2012 to 2017 for the development of infrastructure for research facilities. And finally, I would like to mention here that from 2015, our department several times has been ranked number 1 in any Indian universities. several times. So with this, again, I welcome you all to this program, the fixed point problem, the old and the new under GIAN program. Thank you.
Thank you very much, sir, for giving a brief sketch of the historical development, establishment of the Department of Mathematics, a seminar, and the Aligarh Mathematical Society. That was and we are here as number one by the many rankings of the agencies. So due to our teachers and the scholars working regularly day and night, may I request the volunteers, the scholars, please make possible to the sitting of the teachers coming from the various departments and the participants also. Please, scholars, make possible it. The Aligarh Mathematical Society is very, important society for us. However, today we are not having that society. I will request on behalf of the scholars and the students of the Department of Mathematics that Chairman Sahab, please, under your guidance, this society should also be revived. In 2014, it was revived, and it is my privilege that I was the elected vice president of the society. Now I request the very dynamic young, the course coordinator, Dr. Javid Ali, to present, to show or introduce this particular program, the GIAN program on the fixed point problem, the old and the new one. Dr. Javid Ali.
Respected Vice Chancellor Ma'am, Professor Naima Khatun, Professor Chief Guest of the today program, Professor Amine, Professor Sartar Tabassum Sahab, Dean Faculty of Science, Professor Shahid Ali Sahab, Chairperson Department of Mathematics, Professor Mohamed Imdad Sahab, Guest of Honor of today program, and my teacher and my PhD advisor as well, and Professor Viva Sharma Ma'am, Local GIAN Coordinator of this program, and my teachers here, my colleague and his friend and participants. First of all, good morning all of you, and Assalamu alaikum. So we are basically organizing this program under this GIAN series. So this is one of the important program initiated by the Ministry of Education, Government of India. So I talk about particularly this theme, fixed point problem. So this is a very important research area in analysis due to its various application in the different branches of mathematics, not in mathematics, outside the mathematics. And still this area is very important. In last ICM, it was held in the Brazil in 2018, and one of the professor from MIT, Professor Constantinos, basically got a very important or prestigious award after the field medal Rolf Nobelina Prize. And basically he used generalized version of the Browder fixed point theorem to study the basically complexity of the algorithms appears in the Nash equilibrium problems from GIAN problems. So after the field medal, this is a basically second prestigious award in mathematics. So still this area, fixed point problem or fixed point theory, is very important area. And of course nowadays we have era of the AI and machine learning. So of course they deals with the different kind of the algorithms. So they always interested to basically check their stability analysis, convergence behavior, and of course in coming days this area will explore more. So in this thrust area, fixed point theory, we have also fixed point iteration or algorithm. We always focus to study the basically convergence and stability analysis of such kind of the problem. So of course first of all we study the existence part, means whether the particular operator has a fixed point or not. Fixed point means any point which is invariant, simply layman language, any element which is invariant under any transformation. That is very simple. So that's why for the future point of view, this area is very important, especially for the AI and machine learning. And people are using this area in engineering, especially in the electrical engineering, mechanical engineering, computer science, and other areas. Even yesterday we had basically one colloquium talk. In that, Professor Khamsi explained or solved the basically very important problem for the, from the physics, Dirichlet energy problem. So of course they solve the problem in some particular setting, but still we have some solution for that problem. So that's why basically we fix this title, old and new. So of course because this program generally participant for this program basically from the, you can say, fixed point background or related analysis area, but important thing is the new one. So in the next 5 coming days, Professor Khamsi will basically explain what are the basically new challenges and what are the basically new problems in this area. So that's why we choose this title, the old and the new. So what is the new in this area? So this is important area. So I again thanks to the participants and all this one, and I again thank to the basically dignitaries on the dais to come join this program, inaugural program of this GIAN course. And so let us enjoy this 5 days with this special problem, fixed point problem. Thank you very much.
Thank you, Dr. Javid Ali. Obviously, this is a very fundamental problem, the fixed point problem. You know, Dr. Javid Ali showed various applications of in different fields, not only in mathematics. There is a very important incident I will share here, that the fixed point touched each and every field, each and every branch of the mathematics. Even if I'm working in the field of relativity, I remember that in 2003, it was the conference, ICM, where the field medal, the second important award after the Nobel Prize, was given to Gregorio Perelman. Gregorio Perelman was given the field prize for solving the Poincare conjecture, the $1 million problem. He used the theory of R.S. Hamilton. He is a physicist, R.S. Hamilton. He developed the theory of the geometric flow, the flow of the geometry, and very particular solution of that geometric flow was the self-similar solution. The self-similar solution are nothing but the fixed point solutions of the geometric flow called as the Ricci-Soliton, and that after the solving that Ricci-Soliton, Perelman solved that $1 million problem. So this is very important problem. Here I would share one line about Dr. Javid Ali. He is very dynamic. You know, he is my contemporary. He is very young. But it is incomparable in the sense that he always contribute to the department, not only the department, in the country. At international level, he participate everywhere where he get the chance. You see, by his keen interest in research, he almost flied and covered the 25% of the globe to make a collaboration, international collaboration with the mathematician. This is very, very appreciated. फिर से मैं रिक्वेस्ट करूंगा स्कॉलर से, स्टूडेंट से कि जो टीचर्स हमारे वेरियस डिपार्टमेंट से आए हैं उनके लिए प्लीज़ सीट का अरेंजमेंट करें. हमारा कॉन्फ्रेंस हॉल छोटा है और ये बहुत इंपॉर्टेंट है. दिस ब्यूटीफुल गैदरिंग इज ब्लॉसम बाय वेरियस टीचर्स and researchers from each and every department. I am seeing engineering faculties are here, the faculties from the industrial chemistry and chemistry is here, and from every department, from administration, there are lots of people here. So it is very beautiful gathering. Please, student, make an arrangement. So now, because Madam has a meeting, very important meeting, she suggested and asked her she want to deliver her address before, because it is usual that the chief patron of the program is delivers his speech in the last, but with utmost respect. Now I respect the Honorable Vice Chancellor to present her address and share her insightful thoughts with us. Thank you. Ma'am, please.
Assalamu alaikum and a very good morning to all of you. The chief guest of the occasion, Professor Amine Khamsi from the University of Texas, guest of honor, Professor Imdad Saab, the Dean Faculty of Science, Professor Sartaj Tabassum, and the Chairman Department of Mathematics, Professor Shahid Saab, and the local coordinator of the GIAN, Professor Vibha Sharma, and the coordinator of this program, Dr. Javid Ali, and Dr. Musawwir Ali, who is conducting the program very beautifully. First of all, I must congratulate the Department of Mathematics for always being ranked 1 in our country, and in almost most of the prestigious international ranking committees have always put the Department of Mathematics in a very high rank. So for that, the faculty members of the department, the researchers and the students, they really deserve a big applaud for that. I'm happy. And the department has, as the chairman Saab has just has described the illustrious past of the department. The department is established much before the university was established. The university got its rank of university in 1920, but since the inception of the MAO college, the need for the Department of Mathematics was felt, and the very renowned personalities like Dr. Ziauddin Ahmad, Dr. Chakravarti, and Dr. Majid Qureshi, they were the initial professors, they were appointed in the Faculty of Mathematics. So it has a rich and glorious past. So when this GIAN program, that is as part of the Ministry of Education, Government of India, they have introduced so that the faculties from far off place, from Western countries, from very prestigious universities, they come and the students get the chance, the researchers and the students, they get the chance to interact with the trend of the discipline. So this is what is being that Professor Amine Khamsi Saab from the university, though from Moroccan origin, from the University of Texas. So your illustrations, your speeches that you were going to deliver, I am sure the students and the researchers, the faculty members will be benefited by your lecture. I welcome you to Aligarh Muslim University. And as you know, Aligarh is a small city. We have our own limitations. So I hope you will stay, you will stay and you will enjoy your stay in the university. And you'll appreciate the efforts that are being done by the Department of Mathematics in the field of academics. And as we all are aware, this department has its contribution all over. And as it is the discipline of mathematics, sometimes known as the mother of all disciplines, like philosophy, similarly, mathematicians are known for simplifying the problems which are complex. So I hope the experts, the resource persons from various parts of the country and from US, they will give you the basic teachings or the problems that are presently prevalent, like Dr. Musafir and Dr. Javid Ali has just mentioned. Now it is the days of artificial intelligence and machine learning algorithms. I am ignorant about the discipline of mathematics. I have no knowledge about that. But these problems are these days are used in many disciplines, like in electrical engineering, electronics, computer engineering, computer science. So these days, every time we hear about artificial intelligence and about machine learning and whatnots. So I hope this seminar is going to enrich the students, the researchers, and I urge the students to get the maximum benefit out of it. Please try to attend all the lectures that are being organized. don't miss the lectures. Sometimes one lecture is equivalent to 100 books that you go through in the library. So just make it a point that you attend all the lectures carefully so that you are benefited out of this seminar or the conference. I once again congratulate Dr. Javid Ali for organizing things. As Dr. Musawwir has just mentioned, he is a very young and dynamic mathematician and doing very hard work. I wish you all the best. And I once again congratulate the Department of Mathematics for organizing such a fruitful seminar. Thank you very much.
Thank you, ma'am, for your motivating words. You know, I'm again saying that madam has a very important meeting, and in the morning she called me and said, Musawwir, I regret, I cannot come because it's important. But I said, Dr. Javid is very young and first time he is organizing such a conference in the department. It will be very motivating for you, for him and for all of us. She came, and thank you very much, madam. Now it's the time to call upon Professor Bibha Sharma, the local coordinator of the GIAN program. I request ma'am to share shed some light on the concept and vision of the GIAN initiative taken by the government of India to advance the higher education in India. Ma'am, please.
Thank you very much, Dr. Musawwir. Assalamu alaikum, adab, good morning. Honorable Vice Chancellor, Professor Naima Khatoon, our foreign expert, Professor Amine Khamsi, Dean, Professor Sartaj Tabassum, Chairperson of the Department, Professor Shahid Ali, Guest of Honor, Professor Imdad, GIAN Course Coordinator, Dr. Javid Ali, senior mathematicians sitting under one roof here, budding mathematicians, various teachers, senior teachers present here. I can see Sabir sir, Mursaleen sir, Proctor Saab. Once again, I wish you all a very good morning. I welcome you to this beautiful event. And I feel privileged to be present here because this is my first day in this department. I've stepped first time in the mathematics department, despite being part of this university for more than 30 years as student and teacher now. Probably because I was always very scared, and that is why I'm not part of this subject. But I feel very proud of the fact that our Department of Mathematics is one of the gems of not just the academic network on the planet, as well as the country. It's a wonderful thing, and I think we really are very proud of this fact. We all deserve a big round of applause. That has been appreciated, but I can see mathematicians are not interested in clapping for themselves. So, as a local coordinator, my job now onwards will be to keep hopping from one GIAN opening to another, and I'll keep trying to find out some common point to speak about myself and that subject. But I'll not do that. But I must take this opportunity, especially today. I don't know, I may sound very ignorant, but I happen to teach a topic called Frege's Para 62, a book which is Foundations of Arithmetic written by Gottlob Frege. He was a philosopher and a mathematician, and this is a topic which I teach in my philosophy of literature class. And when the fixed point problem came, what struck me was that something I discuss in this Para 62 is the question of numerical identity and language. So that is something very interesting, and I think that's a common point between literature and Department of Mathematics. And many a times I feel that mathematics takes us to a very infinite points where literature also fails in its expression as language. So it's an honor for me to stand here as a representative of the global initiative of academic networks, being the local coordinator, because this is a wonderful program which looks at the entire community of academicians, philosophers, entrepreneurs, and scientists across the globe, and think of bringing them into one network, especially in Indian universities. And this program has been very successful in India. A lot of brilliant scholars, scientists, mathematicians have come to our universities. Our students, teachers, and various people have benefited. The research index has gone high because of that. And this is a very important networking that has been supported financially as well as logically by the government. So it is a program that is worthy of praise, and we are very thankful for governments for taking such initiatives. I am happy to share with you all that so far our university has conducted 22 GIAN programs, and we are still going to have many more. I must also make an announcement to the people present out here that in this month, this will be opening up again for seeking applications. So I invite all of you to please, faculty members, to please come forward and apply as much as you can, because this is very important to apply also, because when a lot of applications reach to the national level from one university, then it also places us on a certain kind of record that we are very much outgoing, very much interested. And though we may not get all the projects, but it creates a pressure that we are very much keen. So you should keep a space for us, a special space for us. And that's what we are benefiting from. Now, very interesting thing is that this abbreviation GIAN has another meaning. It's a Sanskrit word also, which means GIAN, which means knowledge. And knowledge is a continuum. Knowledge is a big mass, which can be entered through various gateways like science, mathematics, social sciences, literature, philosophy, drawing, computers, technology. But we all have to meet in that continuum of knowledge. So I think GIAN proves that through its abbreviation as well as through its full term, that our goal should be ultimately to seek knowledge. Quest for knowledge is more important than to choose what medium is that. And I urge the Department of Mathematics to open its gates and windows and doors to more and more people from this university also, so that various other things can also be benefited from you, because your research index is so high. I know about Professor Mursaleen and various other teachers sitting here that you have wonderful research index, citations. So how to practice these things, how to benefit from these things, and how to emulate your example is also worthy of learning from all of you. So I think that more and more collaboration, inter-department, inter-university, and international are needed to strengthen the global initiative of academic networks. So with this, I take leave. I will not stand here more, but I wish all the best to Dr. Javid Ali, the chairperson of this department, Professor Shahid Ali, and each one of you for having this wonderful program as the first program of this year's season of GIAN at AMU. So have a wonderful 5 days ahead. I wish you all the best, and I'm available for anything that I can help out in. And I thank Dr. Musawwir Ali for the wonderful conduct of the program. Thank you. Khuda Hafiz.
Thank you very much, ma'am, for these beautifully spoken words. Yes, okay. Okay. Thank you very much, ma'am. At least the convener of the program should come. Please. Okay, thank you very much, ma'am. In her address, Professor Vibha Sharma mentioned some key points. I pick one, that she said there is a beautiful balance, almost she said, a beautiful balance between the literature, art, culture, and mathematics also, because there are lots of examples I find. The example of Leonardo da Vinci. He was a mathematician, but he is known as the very famous artist. A field prize winner, Professor Bhargava, is field prize winner in the field of number theory, but he is a very good piano tabla badak. And Professor Izhar Hussein's quote, my supervisor, Professor Zafar Hassan, generally shared it. He said that when the mind tends to heart, the mathematics comes, and when the heart tends to mind, poetry comes. So there is, beautiful saying. So Professor Vibha Sharma is the local GIAN coordinator. He is serving various responsibilities of the university successfully. She is mentor of the University Drama Club at present. She is the deputy DSW. She is the member in charge of Public Relation Office, and now she is the local coordinator. Thank you, ma'am, for coming here. So now it's time to, for me to call upon Professor Sartaj Tabassum, the Dean Faculty of Science, to address this august gathering. Sir.
Thank you, Dr. Musafir Saab. Professor Naima Khatun, Vice Chancellor, Aligarh Muslim University left. Professor Amine Khamsi, our chief guest of the function or GIAN program from Texas University. Professor Imdad Saab, guest of honor. Professor Vibha Sharma, local coordinator of GIAN. Professor Shahid Ali Saab, Chairman, Department of Chemistry. Professor Javid Ali, GIAN coordinator. Distinguished faculty members, other renowned mathematicians, participants, and faculty member of the other departments, ladies and gentlemen, very good morning and Assalamu alaikum. I, on behalf of Department Faculty of Science, welcome you all. I am thankful that you have spared time in spite of your busy schedule, especially our chief guest. He has traveled from there and he will continue this program for, I think, few days. And as this Professor Vibha Sharma has already mentioned about the GIAN and the significance and the contribution, I congratulate to the Department of Mathematics as a part of this GIAN team. And I can say a few words because it is difficult to say a fixed point problem, because in general we have a concept that the problem is fixed, then there is no problem. But here it is a problem when something is fixed here, then there are a lot of problems. Okay, so just we'll see that what is happening, that the old and new, this is also, it is coming from the backside, legacy side, and coming toward the youngsters. Really, but I think it's a very, very interesting, because this is a bridge between the literature and the mathematics, or you can say the applied sciences. Here, I am very, very happy to mention that this Department of Mathematics is one of the best department of the faculty. We are have the 9 departments, and they are maintaining their legacy, their system continuously, their ranking, and all these young teachers are continuing their research in a very proper way. They are sincere, and I hope that they will continue this legacy and take this department to the heights. Here I can say that I congratulate to the organizer, Faculty of Science, all the participants, their dedication, making this initiative success. Your efforts are continuing to a stronger and more dynamic and globally connected education. I am very sure that this GIAN conference and the other seminars, there is a difference between these. Because when we are attending the normal conference, there is a speaker giving his talk and having the limited time. And sometimes several questions, you know that always we have an announcement at the end of the lecture that we are shortage of time and only one question or half question, you can discuss anything during the tea. But this GIAN is giving really a very good and a good platform where you have your expert with you for a long time. You can discuss your problem, you can discuss your collaboration, you can discuss your all kind of exchanges, whatever you have in your mind. And what is the problem, what you think that to do in future, you can discuss with the expert, which is a renowned mathematician. Here you can say in another GIAN program, there are always a expert scientist that's coming from outside and from abroad. I think this is the beauty of this GIAN program, and I am very sure that you all will utilize this chance and this opportunity to increase your knowledge, and you will yield very good result after this successful event, and you will publish good publication, means good publication after this conference, and you will continue your exchange with this, with the group of Khamsi and other scientists wherever you can. So at the end, I can say that I extend my best wishes to this event and hope the discussion and collaboration fostered here will continue to inspire innovation and excellence in academia. Thank you very much.
Thank you, sir. In the last last program of at National Mathematics Day, you spoken very well on mathematics. Now also you spoken very well. I think that regularly you are taking much interest in mathematics. Thank you, sir. You know, many of us cherish the insightful classroom teachings, the profound lectures, and the approachable nature of Professor Mohamed Imdad. Before I invite him on the dais, I will read a short citation. Professor Mohamed Imdad served as a professor and chairperson at the Department of Mathematics, Aligarh Muslim University, India. His academic background includes a PhD in mathematics with his thesis entitled Some Contributions to Fixed Point Theory. He has received several academic awards, including the Ziauddin Gold Medal for his MSc performance. Dr. Imdad's research interests focus on fixed point theory in ordered metric spaces, fuzzy metric spaces, and best approximation theory. Among others, he has published more than 300 research papers in leading mathematical journals and has supervised 20 PhD and several MPhil students. Additionally, he has been involved in international academic collaborations and has served on the editorial board of several journals. Apart from the research, he was very popular among the students for his teaching. We were always allowed to discuss, even in sports, even philosophy, even physics or the metaphysics. Professor Imdad, the floor is yours. Thank you. Sir, please.
Respected dignitaries on the dais, which includes our local GIAN coordinators, Professor Sharma, our Dean Faculty of Science, Professor Tabassum, our guest of our chief guest, Professor Muhammad Amine Khamsi, and our chairman, Professor Shahid Ali, and then one of my colleague, Dr. Javid Ali, who is my student also. In fact, I will begin from where Dr. Musawwir has spoke about me. I don't think I deserve anything like this. Maybe, I don't know why he said it. Maybe he has association or affiliation with me. And that's why he's saying I am a very ordinary, very common kind of teacher, but always doing whatever I can, not as if I'm running away from my responsibilities. Only thing that I try to abide the rules and regulations, and also I was doing my work, job, whatever is assigned here, very sincerely. That is what only qualification I have, that I have adopted my limited sincerity to my duty, whatever was assigned by the university. I will start from the observation of Professor Dean Faculty of Science, our Professor Hazrat Tabassum. In mathematics, when problem starts when problem is fixed. Maybe he is saying otherwise, beyond mathematics. And I can substantiate my viewpoint by saying that mathematics has, recent past has seen the solution of two great conjectures of mathematics. And almost about 350 years or more than that, maybe 370 years, two problems in mathematics. One is Poincare conjecture, which comes from the domain of differential geometry, and Fermat's last theorem. They have challenged the mathematicians for more than 350 years. And this was solved after 350 years, and both solved in positive. Because when there is a problem, genuine problem, in mathematics it may have a solution, it may not have a solution. So if it may not have a solution, we try for counterexamples. And so these two problems, even they have defined generations of mathematicians. So today I don't want to talk anything about my colleagues because I am not competent, neither I have the kind of observation or vision I can't talk to my colleagues. I want to talk to my younger generation. Only two things. If in fact the responsibility of a young is more than the responsibility of a senior person, because he is aspiring to undertake the job. Like teachers, like persons who are like in our state, they are no more useful because they have done whatever, we have played their part. Like Sachin Tendulkar was a very wonderful player, but now he is no more active, he cannot do anything. Sunil Gavaskar was a great player, but now he cannot contribute. Now it is the era of our present generation. So I am speaking, I am just dreaming, this is my dream, that we must have some stalwarts from our younger generation, because our university has not seen a stalwart for quite some time. How long we can recall Professor Irfan Habib, or how can I long recall Javid Akhtar, or how can I recall Shakil Badayuni, or anything like this, Mezaj, whom Tarana will enjoy after some time. So we need the person. So I dream, this is my dream, maybe it come true, it may not come true, but I aspire that we must have some personalities from younger generation, our younger generation, who may be very useful to our country, and even our younger generation from the university, from whom we can introduce our university. As I have said, that the stalwarts, like in the past when I came here as a student, there were many personalities in the university. Now there is a dearth of personality. And I recall, and it comes to my mind to read the great lines of Allama Iqbal, because this has one relation. That when I was in school, this line was written in my college. I was doing my intermediate in HR Inter College, Khalilabad, that is Basti, now Sant Kabir Nagar. So at the back of the chemistry lab, these two lines were written in Hindi in my childhood, and those lines were, हजारों साल नरगिस अपनी बेनूरी पे रोती है, बड़ी मुश्किल से होता है चमन में दीद और पैदा. So what is it? And look at this very college, I can recall you, these lines were there on the back of the chemistry lab, and just near to this we have RSS camp. Look at, which is not possible now. In my college, HR Inter College, Khalilabad, Basti, there were also RSS camps, because they have the training, and there is no problem because we have a school also in our college. So I aspire and I want to say to my younger generation, ये हमारी नरगिस कब तक बेनूर रहेगी? कुछ तो नूर होना चाहिए, का तो नरगिस का फूल उगे जो जिसमें नूर हो. So this is my desire. Obviously, on the other hand, what we can do, I will recall the hard work of Albert Einstein. Look at the philosophy of the Albert Einstein. Whenever Albert Einstein was praised, he was receiving appreciation, he said, no, nothing. I am no more different person than any common person. Only thing is what I have utilized my time better than most of you. So Albert Einstein was always of the view that I have utilized my time better than you. Not that I am very talented, I am something extraordinary, it is not the case. And everybody knows that the devotion and the hard work of Professor Albert Einstein. He was very, very hard working. And probably we are not doing that, we are not utilizing our time properly. And our devotion is somewhat, is not of that caliber or that level. As you know that, जिसको हम लोग कहते हैं जुनून चाहिए, we don't have that very thing. So some of you, some of younger persons, they must come out and create some stars, like we have mentioned, our stars for by their performance, we feel privileged, we feel proud. Even today, we mentioned sometime Professor Irfan Habib about his work, and as if he has the recognition beyond the campus. And what I am saying is what that our colleagues, some of the colleagues may have the recognition beyond the campus, because from whom we can introduce ourselves, our university. So in this regard also I have a couple of lines from a recent poet, that is Iqbal Ashar. While these things have been said, that the hard work is the key. So if you want to have the hard work, you want to do the hard work. Your duty is to do the hard work. Like I go to the class, I work hard, maybe I am not a very effective teacher. I know many of my teachers, they were not considered, or they were not liked in a way they should be liked. Like Professor Mohsin, I may recall here, I have a great respect for him. Personally, I have a great respect for him. He used to come in the class right now, as soon as the bell is gone, and he used to perform, and he used to work very hard in the classroom. Maybe not very useful to the student. The students are always of the view that we are not getting anything from his lecture. But his sincerity and the hard work, and it is our misfortune that we have not able to get the maximum benefit from his lectures. To my mind, he was the most competent, like Professor Izhar Hussain. Maybe we are very learned, we are doing very good, but we don't have the personality like our teachers, Professor Mohsin or Professor Izhar Hussain. They were very, very different kind of personality. Their personality was very wide open. So in this regard, I have a couplet of Professor Iqbal Ashar, which inspires me to work hard, continue work hard, and his lines are, इतनी आसानी से मिलती नहीं फन की दौलत. देखिए, how you can accomplish this. इतनी आसानी से मिलती नहीं फन की दौलत, उम्र ढल गई तो गज़लों पे जवानी आई. You can, our student can easily infer what I wanted to say. By doing hard work only you can accomplish an excellence. To carry out hard work without success, unsuccess, you don't know. Like our mathematicians has tried for 350 years or 370 years and both got their job done. And look at I remember that when Fermat's last theorem proof was submitted, the board which was checking the proof, they said, okay, the proof is okay, now we agree. But still this needs revision. Like the proof of the Fermat's last theorem needs revision, and it will be repairable. But Professor Andrew's team, Professor Andrew and his team took more than one and a half year to revise the proof. Look at how involved and how complex the mathematics is. The mathematics is very involved, very complex, but definitely wonderful. There can be no doubt about this. And as mathematicians and visionaries has said, that mathematics will not even leave literature untouched. I have heard somebody's address where they have mentioned that even it will be utilized in the literature also after some time. That's what is there. So with applications of all mathematics, not only fixed point theorems. Fixed point theorems is very similar. Why? Because we are all solving y is equal to f of x. Fixed point problem is nothing. We are solving an equation fx equal to x. This is very similar to the solution y is equal to x and fx is equal to x. So this is why it is very wide open. And there are now wonderful applications. Like most wonderful applications, they are seen in economics. Like if I mention the demand function and supply function, they are more concrete increasing and decreasing function. If somebody asks you, some increasing function or decreasing function. Here are the examples. And your Darboux, simple Darboux theorem used to say that market will be in equilibrium because you take any interval has a continuous fixed point property. So any function defined from an interval to itself has a fixed point property. So this very simple theorem says, and this is one of the applications in economics, that market will come once in equilibrium. This very simple thing which we used to teach to our BSc student, Darboux theorem, in our BSc real analysis. So applications are immense, and now mathematics need no mention, no qualification that what are the applications. Now I don't like this question. Why? Because it has already given so much that without mathematics we cannot imagine anything very fruitful, very substantive now, because the simple problems are already resolved and solved. And it is very similar, as Einstein said, that it will not be easy to have good problems. So this is what I'm saying. So my desire is, please come forward and replace our stalwarts. Some of you, maybe we fail. I'm not saying that I'm very successful. I don't consider myself very successful. But I wish that some of you come and achieve that success we intend, that can be useful to the entire community, to the entire country, and above all, whatever you can do. So this was my desire, but that can be only except two things. That only hard work can get you that thing. Without hard work, nothing is possible. So with these words, I say all the best, because we are no more useful. At the same time, I would like to mention one more thing. Like we have, as I mentioned, named the Sunil Gavaskar and Sachin Tendulkar. Okay, one is very talented, other one is not talented. But look at the accomplishment. You can never compare that. Sachin Tendulkar was as solid as Sunil Gavaskar. As you see these days on the social media, many things used to come and they discuss. That one day Sunil Gavaskar mentioned that Asim Akram was not able to get me out ever. Then Wasim Akram said, no, I once got you in a one-day match. And then what Wasim Akram said was very wonderful. That when I was bowling to Sunil Gavaskar, I always find it very difficult what to do. Because if he follow the ball, the ball is moving or getting out or getting in, he follow it. And wherever I used to bowl, so Sunil Gavaskar, I don't know what to do. I have no way to attack him because he was so solid. So the talent, one thing, I want to mention that talent alone will not get you anything. Maybe I see many youngsters these days, and I often see that they are more talented. Like our parent generation is more talented. But they are not having the kind of devotion as Sunil Gavaskar used to have. Maybe you are talented like Sanjay Tendulkar. To utilize your talent maximally, as we talk about maximum element or maximum in many things. So maximize your achievements. That could be the way. I wish you all the best with these words. Thank you very much.
Thank you, sir. As I said, Professor Imdad, you can discuss any corner of not only of mathematics, literature, art, politics, sports, or metaphysics. You can discuss everything because he is a true thinker, and thinking produces you the knowledge, and he has in-depth knowledge. You can discuss. Even after this program, you should attend his lecture. Inshallah, you will learn many more. Once again, I'm very much thankful that there are lots of people who have either love with the speakers or chief guest or guest of honor, or with the coordinator of the program, or with the department or with the subject. I see there are lots of important faces here in this gathering. Life Science, Dean Faculty of Life Science is here, Chairman, Department of Industrial Chemistry is here, and my friends Murad and Dr. Yasir, Dr. Rashid is here. A senior professor are sitting. I see Professor Saeed, supervisor of Professor Mohamed Imdad is here in the last row, I think. Thank you, sir. Now it's a time to listen a distinguished mathematician, our chief guest of the function, Professor Amine Khamsi. We eagerly are waiting your inspiring words, sir. Before I invite you on the dais, I will read a short citation. Professor Mohamed Amine Khamsi is a professor at University of Texas, El Paso, USA, and at the Department of Applied Mathematics and Sciences, Khalifa University, Abu Dhabi, UAE. He earned his PhD in mathematics from the University of Paris in 1987 in the area of fixed point theory in Banach and metric spaces. Prior to that, he obtained MSc Mathematics in 1984 and a BSc in Engineering from École Polytechnique, Paris in 1983. He also served as a joint professor at King Fahd University of Petroleum and Minerals, Kingdom of Saudi Arabia, 2009 to 2021. His research interests include fixed point theory, the geometry of Banach spaces, discrete dynamical systems, and logic programming. Professor Khamsi has been recognized among the top 2% of scientists worldwide, Stanford University, ranking of the Stanford University, and has received awards such as the Best Research Project Award from King Fahd University, Petroleum and Minerals, and Distinguished Science Award. He has published more than 200 research papers in reputed journals and authored several books including fixed point theory in modular function spaces and an introduction to metric spaces and a fixed point theory, and served as an associate editor for various mathematical journals. Professor Khamsi has supervised several PhD and postdoctoral students globally. Now, sir, please come on the dais.
Assalamu alaikum. It is really an honor to be here today. This is my second visit. When Javid told me about it and he insisted, I told him, I am so busy, you have no idea. In fact, yesterday I was teaching online to my students, and but I wanted to come. And I was telling Izhar, inshallah, next year I will be in Jamia Islamiyya, inshallah, okay? Quickly, I am not gonna have a speech, nor that I will talk after these distinguished speakers that spoke before me. What I wanted to say is, as a parent, we usually, all of us, no exception, wherever you are, regardless of your religion, you all struggle to raise your children to be better than you. And I really commend this initiative, Professor Viva. This initiative is wonderful. And the essence of this initiative is for you young mathematicians, whether you are a student or an assistant professor. It's for you not to talk about us, the experts. It's for you to be better than us. And that is the message I want to carry during these next 5 days. Thank you very much.
Thank you, sir, for this crisp speech. Now it's a time to vote of thanks, because the program is almost towards its end. I invite हमारे हरदिल अजीज उस्ताद प्रोफेसर कलीमुद्दीन अहमद साहब for a formal vote of thanks.
Thank you very much, Dr. Musawir. Dean Faculty of Science, Professor Sattaj Tabassum Sahab, Chief Guest of the occasion, Professor Mohamed Amine Khamsi, Guest of Honor, Professor Mohamed Imdad Sahab, Chairman of the Department of Mathematics, Professor Shahid Ali, Local Coordinator of GIAN, Professor Viva Sharma ji, Course Coordinator of GIAN, Dr. Javid Ali, colleagues and students of the department, dear participants of GIAN course, and all those who have come to attend this inaugural function, very good afternoon, and still it is good morning to all of you. Indeed, it is an honor for the department that one of the leading mathematicians, Professor Mohamed Amine Khamsi, from the University of Texas, USA, is going to deliver a series of lectures to participants of GIAN course for a few days. We are thankful to you, sir, for taking so much pain of traveling and coming to our department. I am sure your stay will be very exciting, beneficial to students from learning point of view. Hope participants will improve their GIAN, knowledge in this field of research. Apart from Professor Khamsi, Professor Mohamed Imdad, a former faculty of the Department of Mathematics, shall also enlighten our participants. We are also thankful to you, sir. I personally consider such type of courses entirely different from conferences. It is more focused and gives ample opportunity to participants not only to learn subject but also to start research in this particular domain of research. A special thanks to course coordinator Dr. Javid Ali for conceiving the idea of this course and inviting a luminary in the field of research of the theory of fixed points. Perhaps this is first GIAN sponsored course in the Department of Mathematics in last 8-9 years of inception of GIAN program in India. I am thankful to Vice Chancellor Madam who made it possible to come to inaugural program, Dean Faculty of Science and GIAN local coordinator for their presence and valuable suggestions and remarks. Also thankful to all participants of GIAN course, students of this department and colleagues who made possible to attend the inaugural function. Once again, thank you one and all. Thank you very much.
On behalf of Department of Mathematics, I also thankful Professor Kalimuddin Ahmad for presenting his vote of thanks. Now it's the time for, again, for the following the traditions for national anthem and Tarana. Please.
Hello, 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 hello. Hello, hello. Hello, hello. आ रही है? हेलो, 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 हेलो.
दावत खाना पहुंच गया नीचे है इतनी
Hello, hello.
Do we have chalk? Oh, perfect. Oh, perfect. Perfect. Okay. Yeah, of course, of course. Thank you. Thank you, Javid. Perfect. Come here, come here. Okay, so shall we start? Okay. So, first of all, I'm glad to see you all and to see young faces. Is something that is becoming more and more rare in mathematics. Young people do not want to do mathematics. I was telling people during the tea, I have 5 children, they are all grown up, and none of them wanted to do mathematics. They said, Dad, you don't make money, we don't want to do mathematics. So it's very hard to get young people to get interested. It's a struggle. Whether it's in the U.S. or now at Khalifa University, we're having major problems recruiting young mathematicians. We have a very, very interesting scholarship at Khalifa, and still we are lacking people applying, quality people applying. Okay, so you heard a little bit more this morning during the opening ceremony about this course will be about fixed point theory. And even some people tried to motivate you by telling you that fixed point theory is very important. And basically what it deals with is a problem of finding solutions. So you try to formulate your problem in a way that you are looking for a solution and the solution is interpreted as a fixed point. And you have, in this situation, few questions, natural questions, which is number one, do I have one solution or more than one solution? Number two, what can you tell me qualitatively about the solution? This is typical, for example, in chaos theory, bifurcation, and so on and so forth, dealing with solutions to differential equations. In fact, somebody was asking me right now about what does it mean to be an equilibrium solution and the solution of a dynamical system. So that qualitative approach tells you more about the solution than just a solution, or there exists a solution. And then you have another question, which is how, if we don't know how to find the solution exactly, which is the ideal, how can we approximate the solution? For example, if you look at square root of 2, okay, which is, I call it one of these aberrations or the creations of Allah that are weird, truly weird, all these irrational numbers, because we will never live with irrational numbers. We only live with rational numbers, okay? And if you look at square root of 2, okay, though we don't know what square root of 2 is, okay, because of this infinity of decimals, it doesn't stop, we can still approximate square root of 2. We have a mean of approximating square root of 2, and this is an old problem. The same with pi, by the way, okay? That is almost 3,000 years old. So this problem is still, till today, a valid problem, meaning how do you approximate the solution, if any? Huh? So this course is about the fixed point problem, okay? And I wanted to touch on the origin of this problem, the old, and also some new ones, some new questions. Now, I'm not going to be technical, to be honest with you. Why? Because you can easily read the paper on your own and see the technicalities and go over the proof, assuming the proof is correct. You can go over it, okay, and learn the technicality. What you want is what's behind the technicality. So the last 2 days I have been working with my AI assistant, and I had this discussion with him about things that goes beyond what you can read. He can read all the publications, but he doesn't see what's behind the publication. So when you read the paper, you wonder, what did the author think before writing the paper? So you are doing the inverse problem, getting into the mind of the person who is writing that paper. So what I wanted to do is start from there, go over some. It's going to be a long process, okay? But bear with me. And if you look at the program of this course, me and Javid, we worked on it, and we put some titles for each lecture. I am not going to follow the titles. It's like a flow, whatever it takes me. I mean, if I meet it in the first, well, it's like students when I give them the syllabus for the course, and they start asking me about sections. I told them, this, you can do it on your own. But when you are talking to someone else, you cannot tell him, I'm doing section 3 of the book. It doesn't make sense. You are talking about the content and what you are doing in that content. That's what you want to get out, not the title of what we are doing. What is it exactly that we are talking about? Okay, so let's start. First of all, if I say fixed point theory, fixed theory in general, you are dealing with a few important theorems that started the theory. Okay, so at the beginning it was not a theory. At the beginning it was a tool, okay, used by others. The same with many branches of mathematics, like topology, for example. I'll be mentioning something about it. At the beginning, it was not a theory. It was just some tools that the people developed to use it to understand something. Like topology, it was interesting to understand the concept of convergence, closeness, and so on and so forth, formalism behind calculus, okay? And fixed point theory finds its roots into three main theorems. Tarski, in the discrete case, that tells you any monotone mapping defined on a complete ordered set has a fixed point, okay? That's Tarski. And then you have Browder that says every continuous function defined on a compact convex, locally convex space, compact convex subset, has a fixed point. Okay, that's the one that Imdad was mentioning earlier today with the interval AB, which is the easiest. Okay, continuous function defined on an AB, so AB has a fixed point. And then you have the famous one, which is the Banach contraction principle. So the Banach contraction principle gave birth to metric fixed point theory. Tarski fixed point theorem gave birth to the discrete fixed point theory. Okay, and Browder fixed point theorem gave birth to the topological fixed point theory. Now you have to understand that there are three schools. Okay, and when we meet in this international conference on fixed point theory and applications, the three schools, they get together. Okay, and we start to see how we jump from one to the other one. Okay, communicating with others, because we stay in one area, but then we only focus on that area. Sometimes it's good to jump and see what the other ones are doing. Okay, and we have now dedicated journals in each area. Okay, in each area, we have one called Order. It was done by Rival, but and we have so many of them now in metric fixed point theory. And there is one more Canadian journal of fixed point theory from Canada, that is mostly dedicated to the topology one. Okay? So I'll be touching mostly on metric fixed point theory. So basically, my roots are with the Banach contraction principle. Great. So everybody knows about Banach contraction principle. Okay? Sometimes even it's taught at senior level undergraduate mathematics courses. But for sure, 100%, any master student in mathematics have seen this theorem. Okay? Everybody. And we know the proof. Okay? So the question comes, not me talking about Banach contraction principle from the classical point of view. How can we now look at it with some secrets behind it? Hidden secrets. So this is for the first time you're going to see me talking about this, or maybe even hear about this. So we're talking about the Banach contraction principle that you all know. But what is it behind it? What are the secrets that are behind it? Okay? And believe it or not, there are still secrets, till today, questions that we don't know how to answer. Okay? So I want to excite you to see it from a different what? Angle. Not from the classical angle that you learned when you were a student. Ready? Shall we start? Yes? Okay. So, metric fixed point theory finds its roots into, as I told you, the Banach contraction principle, and it has major implications. Think of it, for example, to the concept of attractors in fractal geometry, or in solving integral equations. Like, for example, this is a for example where you take a differential equation, take it into an integral equation, and the solution becomes a fixed point. Okay? And that's how you start to apply the tools, including the Banach contraction theorem, to solve the problem in certain ways. Okay, so let's go to, first of all, when the Banach contraction principle was published. It was published in 1922. 1922. Question. Okay, because I will ask you a very, very tricky question, which, by the way, my AI assistant failed drastically. Okay, drastically. I will ask you and see how you're going to react. Okay, and at the end, he threw the towel and he said, "Okay, please enlighten me." I'm talking about the AI assistant, not somebody. Okay, you will see. You will see in a second. I posted it, by the way, because it was so funny, his answer, that I posted it on Facebook. But let's go back here. So we understand that Banach contraction principle started in 1922. Okay. First of all, what is the fixed point? What we call the fixed point problem. The fixed point problem, you have a map, T. I'm looking at single values. In this course, I will not be talking about multi-values. Okay? Though it's very shame, multi-valued is more natural, and I will say something about it. So you have a map that goes from A to B, and the elements of A and the elements of B are of the same nature. For example, you cannot have input that is a number and the output is a matrix. Okay? If that's the case, there is no way you're going to have an input equal the output. You can't. Because to have an input equal the output in the fixed point, you need to have the same nature. In other words, A and B, they come from the same big sets. Okay? Same type of element. Okay? Number one. Number two, you want to have something in common. Otherwise, how are you going to have input equal output? So we can assume, which by the way, traditionally we assume A equal B, self-map of A, but we can assume that they have some common thing. Like A and B do have some common point. Otherwise, the problem is ill-posed. So you are looking at under what condition we can find X such that T of X equal X, or the input equal what? The output. Is that clear? Great. Now, this is everybody across the world, everybody over the last, say, 100 years, 1922, 100 years, because Tarski's theorem as well as Browder came a little bit later, but let's say 100 years, okay? Everybody thinks of this problem. But there is something there that they discovered, and you will understand in a second why, that people did not pay attention. So again, what was the goal? What's my goal here? Is to take you behind some of the secrets, not just the technical parts. I'm not going to tell you, for example, oh, this is a fixed point. What is a fixed point? No, no, no. How can we see something that nobody saw before? Something new, because that's what we're interested in. I'm not interested to see what people saw, because what people saw, they already juiced it. They know everything about it. Okay? So can we see something else? So here, this is what I want you to pay attention to. Pay attention to this. So this, in fact, becomes what? Just ignore everything else. Okay? Ignore everything else. And pay only attention to this. To this. So basic math tells you this is an equation. Yes or no? It's just an equation. And what we are trying to do is to solve the equation. Okay. Now, I'm going to call it fixed point equation. Why? Because I have T of X equal X. Is that clear? That's what it is. So I can give you a quadratic equation, ax squared plus bx plus c equals 0. And I can make it what? Fixed point equation by adding x to the left and to the right. Does this make sense? Yes? You are with me, huh? So this is known as, no. I call it the fixed point equation. There is nothing about what? Fixed point equation. We have more about the fixed point what? Let me show you how old. Let me show you how old it is. Okay? It's older, by the way, for thousands of years. But let me just take you to the meaningful historical point. Start from there. Okay? But there is even more to the story. I'm not going to talk about this. terrible. So the man I'm going to be talking about is really famous. And I'm so obsessed by him to a point where he wrote a book. And that book in Arabic. He wrote a book in Arabic. And that book is not translated to English. Okay? And it was only translated to Russian. And people who are working in history of mathematics, they hated the translation. And the reason why, because the Russians added comments. And when you are looking at history of mathematics, you should never add comments to the translation. What you want to do is translate exactly word by word what is like translating the Quran, for example. Translate what the author wrote. Why? Because the people are more interested to go back into, as I told you, the mind of the author. You understand? Once you start putting your words or comments, then we don't know anymore, was it, what's his name, the author, or was it the one who did what? The translation. Okay. Let me give you an example of this. We are like friends here. Huh? I mean, I'm not formal. Don't expect me to give you a formal lecture from now till Saturday. It's very informal, okay? I'm considering you as friends. We can go afterward, have coffee, and we can still talk. And just, we take it as easy as possible. The example I tell my students is Euclidean geometry. Okay? Euclidean geometry. And the best example that I talk to my real analysis students is square root of 2. And the story of Euclid with square root of 2. And what's interesting is that the geometry that you know of, Euclidean geometry, comes from a big book called The Element. Okay? It was written by Euclid. The only problem is that the original version is lost. When the Mongols attacked Baghdad and Basra, they burned all the books. So we lost the original copy. The only copy left to us is the translation from the Greek to Arabic to Latin. And the problem is that the mathematicians, the Arabs, added comments. So the people are no longer clear of what was the problem with Euclid. Specifically, the last part of the element, because he talks about square root of 2 and the problem he had at the end of his life. Okay? And the reason is because he knew that square root of 2 is not rational, but he did not know of what are the irrational numbers. And it was a real number for him. Why is it called real? Because he uses the Pythagorean theorem to show the distance between two things. Now, let's move on. So what is this? This is about approximating sine of 1 degree. Okay? And the reason is, and the motivation is to compute the circumference of the Earth. Okay? And 1 degree, think about it this way. 1 degree is a vertical angle. Let me show you. So you have a right triangle. So if you have 1 degree and you have r on the hypotenuse, what you have here is r sine of 1 degree. Okay? Except that 1 degree is extremely small. Okay? And therefore, if the angle is very small, this measurement will be below the errors in the old days. So you couldn't get a better approximation of sine of 1 degree. So what do you need to do? You need to make r what? You can't control 1. 1 is 1. You need to make r big. If r is big, okay, this number becomes enough that when you measure it, you fall within the, you have no problem with the error
because of your instrument. We're talking about 500 years ago and how they used to do it with sticks. Okay? So the Khalifa of Baghdad at that time, he said, okay, where can we go to have flat surface? Because if you are on a curved surface, geometry now, non-Euclidean geometry, you cannot have a right triangle. Okay? So you need to go to somewhere where you have a flat area, big area, flat. And they went to Central Asia, and he sent 2 teams. Why? Because he wants to do 2 measurements and compare the result of the 2 teams. So you have to send 2 teams to Central Asia. They will do the measurement, and they will come back for the approximation of sine of 1 degree. What did they tell you before? This is important to have the approximation of what? Of the circumference of the Earth. And why are we interested? Khalif was interested if he sends an army in this direction, north. He knew they will come back if they continue all the way back to Baghdad from the other side, because it's circular. So he wanted to know how long it will take them to go from Baghdad back to Baghdad, okay? Without talking into the issue of oceans and so on and so forth and difficulties. But that was his motivation, the Khalifa's motivation was that. So what Al-Kashi did, okay, Al-Kashi came to the Khalif and he told him, I can give you the approximation of sine of 1 degree. Listen to this. I can give you the approximation of sine of 1 degree at any level of approximation you want. As close as you want, without leaving my home in Baghdad. That's what I tell my students. This is the beginning of what? Calculus. This was done before calculus. Okay? Because when you are looking at approximations, then you are looking at calculus. That's how it was born, calculus. Because our friend Newton wanted to find the instantaneous speed instead of the average speed. So the book by Jamshid was called Miftah al-Hisab, the key calculator, or the key of the calculator. Understand? Is the key to use to open just calculations, which is what we call now modern numerical approximation. Okay? So he gave them so many techniques how to do approximation. In fact, he gave them one of the most amazing approximation of pi, okay? That revolutionized what was known before. Anyway, the book that is interesting, I want you to, I have a PDF copy of it. It's the 3rd one, Bergeron, okay? That's a very interesting. It has a chapter dedicated to, he calls it the fixed point result of Al-Kashi, or Al-Kashi fixed point, okay? So how did he do it? This is the point I want to show you. How? First, he established that inequality. Do not believe, oh, this is trivial. He did not have the mathematics we have today. He did not have the trigonometry we are having today. What he had was pure geometry. Okay? So he proved that identity there, sine of 3 theta, here using geometry. I assure you, okay, it is extremely challenging today, not a student, to well-established mathematicians. You give them the proof and tell them to try to explain it. Not to understand it, explain it. Okay? Understand it and explain it. It's extremely difficult, pure geometry. Okay? Anyway, so this is what he did. He put x equals sine of 1 degree, and that equation gives you this. Now, sine of 3, they knew about it. They could approximate it. The problem was 1 degree, sine of 3 degrees. They had tables with sine of 3 degrees, okay, and other angles. But they couldn't do the sine of 1 degree. So what I want you to pay attention now is, look at this equation. That is what? Yeah. Yes? Now, go down to the last one, Al-Kashi iteration. In this book by Berggren, he put this, except my student who did a PhD on Al-Kashi in the States from a mathematical education point of view, mathematics education. It's really very, very interesting. So when we started working, me and him, he was Jordanian, and when we started working on this, that's where I discovered the fixed point equation. So what they are all saying, the authors, okay? They are saying that this is the precursor to what? To Poincare iteration. Basically that he was using Poincare iteration. And in fact, he was not using Poincare iteration, by no means. Okay? So let me explain something first. This is the graph of x, and this is the graph of g of x. And as you can see, they meet. In fact, who was asking me earlier? Oh, you asked me. The graph of f of x meets again. It goes up, and it meets again somewhere. So there are more than one fixed point. It goes like this, and then like this. There are 3 fixed points. What's interesting is that from a discrete dynamical systems, is that this fixed point, the derivative, absolute value of the derivative is less than 1. So that fixed point, this fixed point becomes an attractor. But the other one here and the other one here are not. So they are fixed points, but they are not stable. They are unstable. Okay? And this one is stable, this one here. Now, if I zoom in, okay, you will see this. This does not make sense, and only because what you see, in fact, are the tangent lines. You don't see the graph, the curve. Okay? And the derivative is very small. So, the people thought, okay, it is because it's an attractor, that fixed point, sine of 1 degree. Therefore, we can use what? Poincare iterates, and it will converge, it does converge, to the solution sine of 1 degree. And this way, since it converges, and you are iterating, you can get this approximation as much as you want. See? That's what they thought. But in fact, that's not what he did. So let me tell you what he did. It's very interesting. And that's why I started to pay attention to the fixed point equation, not the fixed point problem. Right? So this is part of the fixed point problem, but it's false. That's not what he did. So what did Al-Kashi do? He came back here, and he said, okay, my x is between, they knew this. It's very small. So they knew about the first decimal, 0 point. Okay? So I did the calculations. In fact, I did them by hand. So your x is 0 point, and then let's call them A1, A2, A3. The decimals. He was not working with decimals. He was talking with sexagesimals, basis 60. That's how they used to do mathematics at that time, but it makes no difference whatsoever. But he was a master in dealing with decimals. A master. I'm talking about our friend Jamshid Al-Kashi. And then what do? You are looking for A1. Yeah? You know this one. Then you use the algebra, and you say, okay, x is equal to 0.81, and they need to find A1. If you plug it, okay, x point A1, A2, etc., you will find A1 equals 0. Once you found A1 equals 0, you go back to your equation, and you look for what? A2. Once you found A2, you go back again, and you look for what? Do you see like an iteration here? So they thought what he was doing is taking an input, put it, get an output. Take the output, put it back, and get the input. That's not what he was doing. He was purely working with what? With the equation. And the decimal what? Development of the solution. Now, do we do this somewhere else? So now we're thinking. On what? On the fixed point equation. Have we seen this before? Yeah. When we are trying to solve a differential equation, and we look for a solution that is a power series. And we're just looking at what? At the coefficient. What do? We plug it, and we start to find what? The coefficient. Many functions are defined and found in this fashion. Solutions like these complicated functions like Bessel functions and so on and so forth, they are found in this manner. Just plug them in, and you will find what? Like an iterative for the coefficients, and you find the coefficients. You are not solving your solution by doing the Picard iterative. No, no, by no means. Okay? So, it's a mistake to think that this is Picard iteration. What you see there is wrong here. Okay, that's not. Okay, so let's move on to the next problem. The next problem is the one that inspired our friend Banach. Okay? So you have this Volterra integral equation. Okay? And you have some kind of, this is typical the end of 1800. Okay? What I call the big revolution, 1847 all the way to 1930. Okay? This is the biggest one that affected us in analysis moving forward. So this is what they were doing. Okay? And keep in mind that X, because we are looking for a solution. And if you are looking for a solution, X is a function. Therefore, the element that you are looking for, not like the one before. The one before, I was looking for X. And X is sine of 1 degree, is a number. Pay attention to these details. Now, you are looking for a function. Okay? A function. You are no longer looking for what? A number. Okay? And therefore, to know where my functions live. So, the space is a space of functions. That is how function analysis was born. Okay? So you are looking for a function that satisfies that equation. Okay? Look at it. You have x here, the function, and here. Therefore, what do I have? Is a fixed point equation. Except that for this one, okay, the work of Javid, Volterra, and Picard, they did iteration. The famous iteration. If you put the right assumption and you start with the function and you start putting it in your equation, okay, then the sequence that you are generating will converge to the solution. So let me explain this before I move a little bit more. It's very, very important that the people, they don't try to grasp the orbit. Let me ignore this completely. Follow me now. What is again a fixed point? Well, I have set A and a set B. I said set A is a set of what? What is the terminology I use? Input, B, output. Yes? And to make it easy on us, let's take the same set, A and B. Just start map. So you have a map. Input, output. You start with an element. Yeah? It gives you what? Image, which is output. So what you do, take that output as input. So generate another what? Output. Take that output back and put it as an input. Yes? And keep doing this. What happens if your sequence converges? Follow me, just follow me to try to understand. What if the sequence converges? So what you have, the input and the output, they go to the same what? Number, the limit. And if they go to the same limit, the input, the output becomes same, which is what? Fixed point of your what? Mapping. Do you understand now Picard iteration? Why is it natural? Why are they doing this? Why are they taking the input, output, take the output back to the input? Why? For this reason, I just told you. No other reason. None. What I just told you is exactly the reason. Otherwise, it stays like what? The orbit, this, that. No, what does it mean? How? Why are we doing this? Now, first example, I was looking for a number. Second example, I'm looking for function, x. So, of course, I don't want to go into technicalities. When I say converge, this is very, very interesting. Let's go back. I told you I want the input and the output what? Converge. What's interesting is the convergence is very tricky. Okay? In what sense? How do you measure convergence? Okay? So, I want convergence, but how do I measure convergence? You measure convergence, which I will be talking about, by computing the distance. Yes? And you want things to start getting closer and closer. Yes? But you see, think about it this way. You have a mean of measuring the distance. What if you have another mean of measuring the distance? Okay? Two tools to measure the distance. You have mean 1, mean 2. What is the danger of this? Is that they can be close with this tool, but they are apart from this tool. So what I want, if I want to secure convergence, the two tools, if I am very small with respect to this tool, I want to be small with respect to this tool. If I am very small with respect to this tool, I want to be small with respect to this tool. Are we okay? Yes? Does it make sense? This is exactly what they call equivalent distances. Equivalent distances are two means of measurement of how close you are, but they are equivalent. If you are small here, you are small here, and vice versa. Okay? But yeah, small, we secure it, but it may take you more with this one than this one. You understand? Which explains this new distance. You see it? So you have the original distance, and you have this new distance. Okay? And your sequence becomes convergent for this new distance. Okay? Because your operator becomes a contraction. Now let's move on. Now, don't worry about it. Okay? Now here is the Volterra theorem. Okay? And it tells you that if you take the Picard iteration, right there, you see it? Right here. The iteration, the input is UN, the output is UN plus 1. Then the sequence converges to the solution to your Volterra integral equation. This is the error that the people saw in Al-Kashi's equation. I told you, it's not what Al-Kashi was doing. It's not. Fine. The Volterra integral equation is connected to our first semester course on differential equations, meaning an IVP, initial value problem. So you take it, you translate it into an integral equation, and you do what you just did. So that's how they solve the differential equation. It's very rare that you attack the differential equation frontal. Okay? We always transform the problem into an integral equation and then move on. Like yesterday, I was explaining the Laplacian equation connected to the Dirichlet energy integral, which basically falls under the same idea. Okay, let's move on. Now, it's a totally different problem, okay? Which is what you do, you have something called iterated function system, yeah? And the terminology IFS is fairly recent, 1981, okay? Fairly recent. But let's ignore this one for a second, and let's here to this one, okay? So everybody has seen this class in your topology class. This is an example of an amazing set. It was discovered by Cantor. This is all 1800, late 1800. They were crazy, okay? I can tell you more about that period of time, which really, they came up with some crazy ideas, okay? So this is Cantor set. but it was known before by Stephen Smith. But anyway, let's keep it counter set. So what do? We take the 0, 1, yes? And then we take the middle, third middle, out. You see it? And then you keep doing this. For every interval, you take the middle, out, middle, out. So these intervals left, okay? Like at the beginning we had 1, next level we have 2, next level we have 4. Every interval will give me 2 of them, yes? Huh? And then they are becoming smaller and smaller. Since I'm using a union of finite number of closed intervals, which is closed. Remember, topology now is there on the real line, not in metric spaces. I had to wait till 1914. I'm talking about on the real line, okay? So they knew that these sets will go down, and at the end we have something left. And that was the contour set, or the classical contour set, okay? So let's go back. So this construction that you see here, okay? Sorry. If you take these functions, look at this. D equals 0, 1. And you take the first function is x over 3. And the second function is 1 over 3x plus 2 over 3. Okay? What is the image of D by S1? What is the image of 0, 1 by S1? It's going to give me 0, 1/3. And if you take the image by S2, you will find 2/3, 1. You see? So the two pieces. So basically what we are doing at every stage, we apply S1 and we apply what? S2. Okay, and we keep going. So we are doing what? An iteration, you understand? Okay, of these two functions. Now, what is special about these two functions? Both of them are Lefschetzian with what constant? 1/3. Yeah? 1 over 3, you see it? They are Lefschetzian with 1 over 3 as a constant of Lefschetz, therefore they are contractions. Therefore the distance or the diameter of these intervals will become smaller. Even you can compute it at every level. Okay? So at the end, this set C at the end, okay, is the limit. We need to be careful. Is the limit of these ones, the ones I just showed you. Sn of E or Sn of 0, 1 is the one we started with. At every level, that's your M. That's here. So at the end, it converges to what? To the contour set. But this contour set, in fact, if you take S1 of C union S2 of C, you end up finding what? C. The self-similarity of the contour set. That was included in the work of what? Of our friend Cantor. He did not know about S1 and S2. He did not know about S1 and S2. Okay? But he knew about these properties. There is more to the story, but what I want to show you is that S1 of C union S2 of C is equal to C. Therefore, C becomes what? S1 of C union S2 of C equal C. Therefore, C becomes what? Fixed point. So now, I gave you 3 examples. In fact, I have about 5 or 6, but I picked 3. In the first one, the fixed point was what? Remember. In the second one, the fixed point was what? Good job. Very good. And the third one is C. Set. Now, let's go back to the second one, the third one. The first one is no problem. Why? Because we know how to measure the distance between two numbers. That is the absolute value of A minus B. Question number 1. What is the distance between two functions? Why do I need this? Remember what I told you. We're doing Picard iterate. And therefore, in, out, in, out, in, out. I want to say what? My sequence what? Converge. How do I see that my sequence converge? I only know that my sequence converges if I can measure how close the elements are, you know, the Cauchy behavior, if you want. Okay? So how close to each other, how small is the distance? I need the distance. Yes? But they didn't have the distance. They had the distance for continuous functions. That was okay with Volterra equation and so on and so forth. But they didn't know how to do it between two sets. Oh, impossible. How do you measure the distance between two sets? How are we going to say that my set Sn of E converge to C? How? Oh, our friend, what's his name? Cantor. Oh, didn't care about this. He did not care about this. He looked at the properties of C, which is really weird because C, for example, is uncountable. It has the cardinality of R, etc., etc. And is what we call completely disconnected set. Anyway, that's not the point I want to insist here. I want to take you to the distance between the two sets. Give me this button. Anybody has another button? No, just a button. There is there. Oh, give it to me. Thank you. So, let me show you something. How people struggled with this one. And we had to wait till 1914 to answer this. Sure. What is the distance? Which is very common. And you have to understand in physics, we talk about distance between planets. Yes or no? Or for example, when you say, I live near the mall, or near the masjid, or near the house of someone. So how do you measure the distance? The way we measure it is this one here. Yes? Yes? Naturally, very natural. The distance between these two sets is this one. Except what? If I tell you what is the distance now? You agree with me? Huh? Common. The distance is 0. But if the distance is 0, the two bottles should be what? No. We have a problem. If you tell me the distance is 0, the two bottles are not the same. And the same goes for planets. It's not like just these two bottles. This people struggled with. Big time struggle. Okay, 1906. Okay. I'm now diverging. It's there, but I'm diverging. 1906. Adam asked pressure. And you find the distance, because in French, he did not use the word distance. He used what we call in French, écart. You don't use the word distance. Say écart, which is the difference between the two. How can we find l'écart, or the distance between two? Wait, 1906. You told us that, what's his name? Volterra, Liouville, others, they did them in 1800. Why do we have to wait for 1906? Because of Lebesgue. Measure theory was born. Early 1900, late 1800, beginning of 1900. It's very interesting to see all this going on at the same time. So now, a function is no longer a function. Function is what now? Is a set. Two functions are equal what? Are equal what? Almost everywhere. So for me, these two functions are, from the Lebesgue point of view, if f is equal to g almost everywhere, the two functions are same. Like what? And this is the separation with what? With the German school. So if you take the indicator of q, 1, q, 0 on the irrational. Yes? This function becomes equal to what? According to Lebesgue, becomes equal to what? 0. Why? Because the rationals are what? Countable, therefore they have measure 0, therefore they are non-existent from measure theory point of view. Yes? Therefore, this function is equal to 0. 0. How can you beat this? It's the best function you can have. Yes? Okay. What do we know about this function? Rationals 1, irrationals 0. What do we know about it? But it's not Riemann integrable. This is the example that Riemann integration and Lebesgue integration are totally what? Fundamentally different. Right there. Okay, fine. Now let's go back. You have a function. It's no longer a function. In the German way, German school way of looking at functions. F of x. No. It's a set. Function is a set. Now I have two functions, f and g. And each one of them is, and I'm looking at what? Between what? F of x, set. G of x, set. And you are looking at what? Do you understand now Adamar's question? So this problem, if you look at it from the distance point of view, is very complex. Chancellor did not do that. Okay? So, we have fixed point, which is what? Number. Fixed point, which is what? Function. Fixed point, which is what? Set. Therefore, when I write t of x equal x, x basically can be what? If I look at the second example, the third example, they have something in common, which is what? That if you iterate, they converge. Not the first one. Not the first one. If you iterate, they converge. When they published Aligarh, Javid, and others, when they did the work on integral equations, and the other guys on what? On sets. They did their work. Each one of them was using tools that in fact were what? I just told you earlier. Input, output. Input becomes what? Back, back, back. They all use the same. But no one saw the other one what he's doing because they were in a different what? Context. Are you with me now? Okay, I'll test you. I'll test you. The AI assistant failed. I will find out about you. Let's move on. Okay, we said metric fixed point theory find its root where? With Banach. And when was it? 19 what? 22. Okay. Banach was part of what's known as, look at the years, 1892, 1945. 1945, that was the Second World War. They all were wiped out. All of them. They were dead. Many of them were Jews, and they escaped Germany's occupation, and they went to Russia. Okay? So some of them died in the war between Russia and Germany, and only few were left in Poland. Okay? By the way, Lvov school is now in Ukraine. Okay, that part is becoming Ukraine today, not Poland. Anyway, so what do you see there? You see what's known as the Scottish book. Do you remember Izhar? When I was visiting Jamia Islamiyya? Do you remember? Huh? It's known as the Scottish book. So I wanted to put it for you, but I didn't put it. What is this? So what they did, this group, I'll show you, maybe they are here. Here they are. These are the brain behind Lvov school, okay? Including, very important, look at this guy. Who is this guy? You see? Anybody sees it? It's in red. What is it? Banach. Can you believe Banach, that the only one we know Okay? And he's standing. Do you see him standing behind the guys? What does this mean? That's why, in fact, I want to show you this picture. Why? Why do you think he's standing? Because the guys who are sitting are what? Are far more important than him. Can you believe it? So anyway, so these people, what they do, they go and they have coffee. They leave the campus. It's a city, huh? It's not like AMU, where you are far from a coffee place. You are in the city. It's like University of Paris. In Europe, the university is in the city right there. So I just crossed the street. I am in a cafe. And they go to the same coffee place called Scottish Cafe. Okay? Which is now a hotel. I found the picture, but I didn't want to put it. So when they go, what they do, it's really interesting, which explains the Scottish book. So what they do, they start talking math. They are mathematicians. Yes? And then they get the enlightenment, a question. And they are, oh, I know how to do it. Oh, how do you do it? Oh, this way. Go this. Oh, I'm stuck. Oh, the other guy will tell him, do it this way. No, this way. These are the best of the best. These are the people who founded functional analysis. You understand? They are the founding fathers of what's known today as functional analysis, or modern functional analysis. Okay? That's what they used to do. They start writing on the table. And who was mad? They start writing on the table. And who was mad? The owner. The owner was mad. Because the table starts what? They move to another table. Once the table is full, they move to another table. I mean, the guy told them, come on, guys, you are destroying my table. So you know what he did? He bought a book. I mean, not a book, notebook. And he put it behind the bar. When they come to have a drink, he will take the notebook and he will put it. And he will tell them, do not write on the table. Right here. Okay, they write. And then he will take the notebook when they are done, and he will keep it for next time. That book is worth millions of dollars. Now, some of them, including Mazur, for example, some of them, they put questions, okay, that they didn't know how to answer. They will write them in the Scottish book. Why? Because the guys who are coming after, they can read it and see the questions and try to solve them. Okay? Mazur, he wrote a problem, 153, I believe, and he wrote, whoever solves this, I'll give him a live goose, live chicken. A goose, not a chicken. Big goose. Yeah? They all died. Mazur was the last one still alive. And who solved it? The problem, whether any separable Banach space has what's known as Schauder basis. And he gave them beautiful counterexample, amazing counterexample. Hard one was Inflow, Swedish mathematician. And he solved the problem in 1972. It's problem number 153. And he was still alive, Mazur, so he had to go back to Lvov, and he was offered the goose as it was written, whoever solved the problem. Of course, Inflow is an extremely famous mathematician that solved some of the profound problems in functional analysis. Okay. Now, let's go back to our Banach contraction. You will see why I'm telling you all this. There is a reason why. So Banach contraction principle. So what is Banach contraction principle? We have a distance, we have a metric space, and we have a contraction. Yes? Remember the famous 1/3 Lefschetz constant? And so what do? You take the iterations. Yes? You understand now the iterations? Always think about it like this. Input becomes output. Output becomes input, etc., etc., etc. That sequence satisfies this. Sure, 100%. Once you have this, then this goes to 0. But this will not be enough for you, because if the next one is closed, does not secure that this and this will be closed. You understand what's happening? There are sequences in R where the next one is closed, but once you go far, you start to go far from this one in the sequence. So I don't want only to have the next one closed. I want to have what? This one and this one closed. Sorry. That's what I want. Are you following me? What I'm trying to explain to you is the concept of Cauchy. The difference between the sequence xn and xn plus 1 are closed, or xn and xm. So this can be closed, but this one will be what? Far. So what you don't want that. Why? Because if they converge, they are all close to what? To the limit. And if they are all close to the limit, they are close to each other. Yes or no? I love you, Wallah, I love you. I swear. What if you don't have the triangle inequality? That's wrong. What I just told you is wrong. Okay. So, let's go to the next slide. You will understand. Next slide. So now, look at the first one. Look at the first one. What did they do? What did they do? Triangle what? Yes. So, doing the math, this, we know how to control it. And then when you do the algebra, you end up having this. But you told me that k is less than what? Huh? Than 1. Therefore, this will go where? 0. Therefore, this will means what? That the elements of the sequence are what? Close to each other. Cauchy. If I throw in what? Completeness, then I have what? Convergence. This is the famous what? Banach interaction principle. Do we agree on this? Sorry. Here is the theorem. This is the theorem that appeared in 1922 in his PhD. Okay. Now let's see. You know the answer. I gave you the answer. Show me that you are better than my AI. Ready? Huh? Ready? For sure. 100%. If you fail, you pay the coffee. I always tell my students. In fact, in America, I even open an account with Starbucks. I tell them, you go, because I can't have 10 coffees in one day. So I tell them, you go and you pay for the coffee under Khamsi's account. Joke. Okay. Go ahead and answer. That was the question I asked. Oh, after we worked, me and him, of course, quite some time, for hours. And then I asked him the question. So tell me now, what made Banach contraction principle so famous? And I'll tell you his answer. Tell me now, you guys. Who wants to tell me? Oh, by the way, do we know the answer? Oh, yeah. You mean we know the answer? No, no, no. You mean today? Yes. Tell me. Who is talking? What did you say? You are like my AI assistant. Wallahi, you are like my AI assistant. Anybody else? Yalla, yalla, yalla. Don't worry. We're among friends here. Don't worry about it. It's not a quiz. I'm not going to give you a grade. This is exactly what my AI was saying. Wallahi, wallahi, I have it recorded, by the way. That's exactly what he was saying. And he was really proud of himself. I mean, I don't know why I say him. I always say, is it himself or herself? I never asked him. And at the end, the one I put on Facebook was, you are like my student. Ha, ha, ha. He was telling me, ha, ha, ha. Yeah. So tell me, guys, what made this theorem famous? So you see, the reason why I'm asking this question, and that's what I was telling the AI assistant. I told him, listen, to answer my question, you need to think outside of the box. What do I mean by outside of the box? How does AI work? Whether it's DeepSeek or Chavid, it makes no difference. So how does it work? In fact, what they do, they get what they call librarian. It's true. They get this librarian. And in America, because they have access to smart chips, NVIDIA, fancy chips, Chinese cannot. Okay, it's illegal to export these chips to China. So what they do in America, they invested millions of dollars, a lot of money, to buy this fancy chip. They put them together, and they create what's known as a super librarian. And that super librarian knows everything. Once he knows everything, and you ask him something, he knows everything. So he can give you the answer from what he knows. He absorbs that knowledge. And he keeps absorbing more knowledge. Okay? Great. What did the Chinese do? The Chinese said, why do I want my super librarian to know cuisine recipes, as well as mathematics, as well as engineering, as well as medicine, etc., etc. What we're going to do, we're going to have different librarians. And everybody is super librarian in certain what? Area. So when you ask the question, automatically DeepSeek will send it what? To the appropriate what? Super librarian. But at the end, both of them, they do the same. Meaning what? Their answer is based on what? On the knowledge. So what did they tell the AI? I told him, think outside of the box. What do I mean by outside of the box? That's what I tell my students. What do I mean outside of the box? Don't think what everybody is thinking. You have to think differently. Something is hidden. What is it? Again, let's go back to the question. What made Banach contraction principle famous? And by the way, do we agree it's famous? First of all, let's agree, because some people, they consider themselves famous and they are not. Okay? Like me. Okay? I'm not famous. Huh? But we do agree, nobody will tell you no, that the Banach contraction principle is famous. Okay? Why is it famous? What made it famous? Go ahead. I'm sorry. No. That's AI. Wallahi, that's AI. I'm serious. Anybody else? Who is talking? Somebody's talking. Go ahead. Don't be shy. Whatever. Wallahi, I didn't hear you. That's AI. That's not thinking outside of the box. So, let me give you a hint. That's exactly what I did with him. I told him, okay, stop. Let me give you a hint. I told him like this, let me give you a hint. Because what he was doing, he will go to the knowledge, and he will give me this list. This, iteration processes, finding solutions, this. Why? Because that's what's out there. Yeah? That's the answer. But that's not what I want to hear. Okay? You want the hint? Let me give it. By the way, the answer is extremely important and powerful. Oh, do we know the answer? 100%. Uniqueness is just one word. Come on, guys. Or if I cut it into two words, uniqueness. Input, output. MashaAllah, wallah, you are good. No. No, I'm sorry. Let me tell you. If I tell you input, output, it defeats. The natural question is what? Why? Yes or no? If I tell you input, output, you're going to ask me why. So when I say two words, they have to have some meaning. In other words, they do make the theorem famous. Otherwise, no. We may disagree, in fact. Yes? Fixed point. No. That's two words. No. Yes? By the way, I'm sorry. In fact. Fixed point. If I go to Tarski fixed point theorem, the answer will be, wait, let me, because I need to explain to him. If you go to any fixed point theorem, like the fundamental ones, Browder, Tarski, all of them, they have fixed points. So it can be valid for the three theorems. But what makes Banach interaction principle famous? Yes? I didn't hear you. What did you say? That's three words. What did you say? Oh, you removed the and, huh? Yeah. Students are really smart. Are you enjoying yourself? Are you having fun? You are? Good job. Allah, I love you. Good job. Really. I love your answer. Who is talking? Who is talking? Lefschetz. Anybody else? Simple applicable. Don't say simple and applicable. You know, after I was done with him, he was lost. The AI assistant. And if you read my post on Facebook, at the end he tells me, please tell me what is. I mean, so it's not. Oh, I have a colleague in Khalifa University. His name is Yohannes. He's a physicist, and he said, Amine, you have to understand that ChatGPT and DeepSeek are programmed to make you, what you want to hear. That's not. He didn't get the point. Why? Because I didn't post the discussion. That's what happened. I did not. I just posted snippet. So you don't get it. Yeah. And he was explaining. He said, yeah, you are right. What he said was profound. I'm talking about the AI assistant. What he said is, I'm sorry, yes, you are right. In other words, I can only see within the box, not outside. You see now the problem where? I cannot see outside the box. And this is the difference between what? Us humans and the artificial. You understand now? We have the ability to see outside the box. So you want to see the answer now? Ready for the answer? Maybe I cheated. Maybe somebody said it and I ignored him. Yeah? Ready? Or you want more time? When was it born, the matrix spaces? I told you. On purpose I did this. When? Does anybody remember? 1906 with Frechet, 1914 with Hausdorff, and the distance between two cells. The formal definition of a distance was born in 1914. Of course, Hausdorff did it following the work of Frechet. Frechet was doing what? Functions, because that was the question from Adama. Okay? And of course he gave some abstract formulation, but it was exactly what? Hausdorff that put it in a formal way, the way we teach it. Axiom 1, axiom 2, axiom 3. Are you with me? Now why does it make the theorem famous? Come on. Hey. Okay, fine. Tell us two words. Okay? Why? You understand? Why? Is it the triangle inequality? I mean, that's axiom number 3. So is that what it is important in that theorem? By the way, I do have Banach contraction principle without the triangle. I talked about it yesterday. So it's not the triangle. Now, connect to the two words. Why the two words made the theorem famous? This is the question. Because we may disagree, by the way, yes or no? Why? Why my answer is, and that's why when I gave it to him, when he said at the end he gave up, threw the towel, and he said, okay, tell me, what is it? And when I told him matrix spaces, he said, I swear, wallahi, this is exactly what he said. He said, I see now. Following what? Not the knowledge, the discussion we're having. He did not pay attention. I was trying to take him out of the box, but he failed. He was still programmed to think the tradition. Now, why? Why matrix spaces made Banach contraction principle what it is? Look at example 2 and example 3. Example 2, the solution was what? Follow me. Very important. I'm repeating myself. I already told you because I knew I'm going to ask you this question. But of course, you did not know what I was thinking. You did not know where I'm taking you. So when I told you the information, you did not pay attention. I didn't tell you on purpose, pay attention to this information because I'm going to ask you about it. I didn't. This happens a lot. You know how much a student will miss from his instructor's lecture? Average 50%. So, second example, what was the solution? Function. Third example. And there is more. When I talk about this point, I give them more. Now, if you look at how we got the solution, I told you that too. In both cases, we're doing the iteration. Pick up. Yes? Except what? That these people are working here. They understood. They use the tools. They use it in other problems, by the way. Yes? And these guys, they use the same tool in their areas. But they did not know that the two of them what? Are using what? What did Banach tell them? You guys, both, are using the same tool. Except one in a metric space where the elements are functions, and the other one is a metric space where the elements are now the kill. Ready for the kill? Ready for the next question? You want to hear the next question? Now they are excited because now they say, okay, now we are thinking outside of the box. Now we know what he means. Huh? Now we are ready. You are ready? Calculus book. How many theorems do we have in calculus book? It's connected. Don't worry about it. Calculus book. How many theorems do we have in calculus book? Roughly. There is no way somebody knows that exactly, but roughly. Can we say hundreds of theorems? I'm talking about calculus book, huh? All of it. Can we say hundreds of theorems? There is one theorem that we call what? Fundamental what? Why is that? By the way, for your information, last month I was interviewing somebody for a job at Khalifa University. And he gave a lecture. And I asked him this question. He was puzzled. He was completely. Why? You see now? There's only one theorem that we call fundamental theorem of calculus. Say it again. In fact, if I push what he's saying a little bit more, The concept of integration is based on two areas. The British school, Newton school, and the German school. The German school was looking at what? At the area problem. Area. Geometry. Newton school was looking at what? The antiderivative. Why? Because of physics. If you have m times the acceleration equal the resultant force, sometimes it's a differential equation, second order, yeah? But how do you solve it? Sometimes you solve it by taking what? The antiderivative, the inverse of the derivative. He is the one who came up with the derivative. Talking about Newton. So the problem of Newton was working on is the antiderivative. Okay? They call indefinite what? Integral. And what these people are working on? The Germans? The area problem. That we call what? Definite integral. Now, one problem is the area problem. One problem is the inverse problem of the inverse of the derivative. And what did the fundamental theorem do? It's connected the two different areas. This is very common in mathematics. Two different problems, it connected them. So what did our friend Banach do? He took all these similar tools used by similar and different people, and he put it under what? One formulation that works for everybody. What formulation is that? Metric space. You understand now? The tools, he did not invent them. He did not. He just put it in the context of what? Metric spaces. Oh, but did he invent metric spaces? I just told you. Did he invent metric spaces? No. It was done by Hausdorff in 1914. Do you understand now? Are you with me, guys? Am I giving you a hard time? Okay? So this is basically the answer why. Believe me, you will never find it published. You will never find this published. Because if it were published, my AI assistant would have what? Answer. You understand? So don't look. You are not going to find it. Okay, so I was telling you this, okay? This is about what? The beginning of the distance from our friend what? Fréchet and Adamach. You have the thesis. I have a copy of it if you are interested, okay? And this is in French, of course. And it's called what? Le calcul fonctionnel, functional analysis, okay? Functional analysis. Great, so then you go to our friend Hausdorff. Yes? Now, quickly, let me just tell you something about him. There where you find dxy equals 0 if and only if, dxy equals dyx, and the triangle inequality. Yeah? And by the way, all what you see there goes back to Fréchet. And for your information, it's a very important step. Okay? People are missing this. Where did they get this? Let me ask you, where did they get these axioms 1, 2, 3? Yalla, who wants to give me this answer? Yalla, Javid, tell me. Have you ever wondered from where they got these axioms, 1, 2, 3? We all teach this to our students. Have you ever wondered what the roots of these axioms, 1, 2, 3? I didn't ask you whether they are valid or not and this and that. I asked you where, because that was published in 1914 in the book by Hausdorff. Do you understand? Question is, how did he get axiom 1, 2, 3? Let me give you a hint. It was done by Fréchet. Okay, he got it from Fréchet's work. Okay, the one I showed you before. From where did Fréchet get this? What was the equation, question asked by Adamach? What was it? I told you this distance between 2, no. Functions. Adamach asked him, what is the écart or the distance? He didn't use the word distance. It was used by Hausdorff to was the écart between two functions. Yes? Where did he get the axioms 1, 2, 3? Okay, I'll help you. How do you measure the distance between two continuous functions? Allah, come on. Defined on AB. Come on, you know the answer. What is it? Oh, wallahi, I can't hear. Soup? La. Give me the answer. So we have two functions defined on AB, continuous, and what is the distance between these two functions? Yalla. It's not max, it's the supremum, yes? Let's go for supremum. Supremum of absolute value of, that's how we found it. That's exactly how we found it. Wallahi, that's exactly how we found it. Axiom 1, 2, 3 is from this. We take a function and we go back to what? To R, f of x, and we look at what? The distance between what? F of x and g of x. How? Absolute value of f of x minus g of x. On the real line, with the absolute value, we have the three axes. You see it now? So he gave it in his thesis. And the other guy formalized it into what? Abstract sets. Okay? What's the name of the book? It's written there at the bottom. What's the name of the book? Do you see it? It's in German, by the way, but the English version. What is it? Basic what? Set theory. Basic set theory. What is it? I mean, he's going to define distance, metric space, with basic set theory. It was volume 1. I mean, not volume 1. Version 1, edition 1. Edition 2. Edition 3, he dropped what? The word what? Basic. It's called set theory. And that book, anybody who does mathematics knows that book, especially in Europe, by heart. It was translated to English sometimes in 1957. Anyway, so it's really funny because the bird of topology is there. There is a chapter dedicated to, he didn't use the word topology. So he gave what was known before in terms of what? I'm talking about accumulation point, interior point, boundary point, ball in a metric space. So you see, abstract topology comes from what? From the topology on the real line in metric spaces, not the other way around. This is what I was telling you about distance between two sets. Triangle inequality. And people started from 1914, moving forward to try to change the three axioms. Okay? You have so many of them. Okay? You have this, and look at the bottom one. The bottom one, when you take g of xy equal max, it leads to what? Ultrametric what? Spaces. Do you see it at the bottom? And this is an exercise that students trivialize. Yes? Ultrametric spaces. So the triangle inequality is no longer plus, but the max. Balls, and how important they are, open ball, closed ball, for the entire topology. And this is the ultrametric. Yes? Huh? Except what? That all the programs, whether in logic programming, AI, computer science, all of them, they lead to what? To ultrametric spaces. All of them, no exception. Why are you telling us this? Because of the work by fitting. Now, if you take a logic program that is stratified with no negation, what happens? In order for you to answer a query of that program, meaning true or false, okay? That program needs what's known as a model. And the model is the set of all these true statements. So when you ask, is this statement true or false, he will check the program if it's inside the model or not. How do they get the model? They get the model by countable iteration. And there is only one model. I just told you. What did they say? I just said it. I just said it. What did they say? How do they get the model? Countable what? Iteration. Iteration. Huh? Iteration. Most likely there is an operator there. In and out. Countable. And how many models do we have? They never understood one. The only powerful tool they had in their hand is substitution. Why? Because everything is discrete. Guess what? Fitting is the one who explained to them why. Because in fact, what they were using is what? Banach fraction. You see it now? How even later on in computer science logic programming, okay, they were using the tools that are inherent to what? To Banach contraction principle. But in order for you to use it, you need to define what there? The two words, metric space. If you don't have a metric space, how are you going to explain that? You understand now? And that is exactly the essence of that paper. Are you with me? The first time somebody told them this, okay? There is more. Yes, I'm going to stop here. Yeah. So let me, is Daj here? Daj? Okay, but he's with us. So shall I keep it for the afternoon? Okay. I will talk about it. Oh, his daughter is here? Oh, what is the daughter of Haji? Oh, I saw your father. Yes, we were having coffee and we were talking, yes? And they told him that like father, like daughter, yes? 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 Yes. So your father made it to my slide. Anyway, so I'll talk about it. Thank you very much. Thank you.
The distance between 2 points is less than equal to maximum of distance between a third point and the first point, and again the third point and the second point. You wrote in this previous slide.
Which one?
In the previous slide.
This is the ultrametric. Ultrametric. Yeah, so this space, okay, every 3 points, okay, 3 points different. They form an isosceles triangle. This the same as this, as this. But again, they exist, but not in a row. No, you have to go to some weird stuff like what they call variation. For example, in computer science, the metrics that are used, they lead to ultrametric. Yeah. And this too, for example, here. He did it only as an initiation, okay? But this work here, these 2 papers, are very important, especially the first one. Sedan and Hisler, they did a lot of work on this. Look at variation theory. Very, very beautiful, by the way. I think I have this paper, if I'm not wrong. Yeah. This is how we're going. Okay. No. Thank you. Thank you very much. So, shall we start? Okay. So, what did we establish? In the first part, we established the importance of the Banach contraction principle. And the role, in other words, moving forward, I have no doubt in my mind, you will never look at the Banach contraction principle the same way as before. Now, you are looking at it with a totally different what? View. Okay? Why is it important? What is it in it? Beyond the conclusion. Beyond the conclusion that was known. It's not like something that Banach discovered. In fact, what I told you was known to Banach. It was something known to him. It's what people try to make it as a conclusion from the Banach. Okay, great. So now we established this. So the question becomes now, how can we go beyond Banach? Again, Banach contraction principle is the concept of these tools implied or used in this abstract form of metric spaces. So people, they wanted to extend it. There were many ways to extend it. One is to extend the Lipschitz condition. Okay? So from 1922 to 1965, people did come up with new classes of mappings. Like, of course, I'm thinking about Canon maps. What's his name? The Gasseric maps, and so on and so on. So there were tons of publications trying to extend the contraction condition. Okay? That's one route. Second route is the metric. How can we preserve? It's the same, by the way, huh? All of them. They all get the iteration that behaves nicely and converged, but the conditions are different. So, for example, can we change the structure, come up with a more general structure? So one route that Professor Dhage has taken, and others, is the idea of looking at an abstract structure, more abstract than metric spaces. Okay? So what's interesting is, first of all, why is that? Why do we want to find, let's not talk about the conditions on the maps. Okay? I will not be talking about this here. I mean, in this course. I want to focus on the structure, the metric space structure, okay? As a continuity to my question, what made him the theorem famous? Okay? What's made the theorem? So, first of all, shall we question the three axioms? Okay? Shall we question the three axioms? When was it published, the three axioms? You know the answer. When? Axiom 1, 2, 3 for a metric space. When were they published? 19? if I give you a quiz now, what's going to happen? Huh? Failing totally, huh? Huh? Wallahi, I came 2 days ago, I ate some very spicy food. My stomach is not feeling well. Wallahi. I swear. It's not feeling well at all. So it was 1914. So remember, 1906 was our friend, what's his name? Fréchet. But Fréchet did not give the axiom 1 and 2 and 3 in the abstract setting with the concept of metric and distance. Okay? It was done in a formal way by Osborne. And again, some people were confused. I'm really sorry. So let me show it to you. Some people were confused about the distance between two sets. They thought that this is the distance. That's not the distance. Distance, let me try to go a little bit faster. See? So, so you see, this is how you define. This is known the distance between the green one and the other one. Huh? So it's the supremum of the infimum and the supremum of the infimum. You reverse it, and you take the max. Okay? So that's the distance between the two sets. This Hausdorff distance is also called Pompeiu. These are the Romanians. They insist to say that it was known to Pompeiu as well. Okay? Okay. So this is based on what's known as the epsilon neighborhood of a set, okay? And you take the supremum of all this. But anyway, so it's complicated. It's not what I was showing you. That's the common sense, but it's not. You see the definition? Huh? Max sup of the two to make it symmetric. I'm talking about this one here. This one. And there is still open questions about it. In the case of multi-valued mappings. Because they assume that both of them are kind of bounded. Anyway, well, let's move on. That's not the purpose of this class. I want to take you to some other level. Okay. Yeah? No, not this way. This way. So, the issue was about questioning axiom 1, 2, and 3. I already talked about 3, the triangle inequality. Okay? What if you don't have the triangle? And you have to understand that questioning axiom 1, 2, and 3 is not like for the sake of questioning. It's not only for the sake of coming up with some more general structure. I'll give you an example and you will understand. Okay? What's known as the flower shop problem in computer science. Okay? The flower shop problem in computer science. So let's say you want to buy flowers. We are celebrating what's the name? On the 14th of February. What is it called? Huh? What is it? What is it? What is it? Huh? You are unbelievable. Oh my, you are unbelievable. So, I'm celebrating my wife's birthday. And I need to buy some flowers. So, I go to the flower shop. Okay? And leaving my home, going to the flower shop. Okay? I can compute the distance between my home and the flower. Question. Will the distance from my flower shop or the flower shop to my home will be the same? Very simple. Yes or no? The answer is it will not be the same. Therefore, the distance from A to B is not the same as B to A. Why? And I gave you the answer earlier. We have axiom 1, 2, and 3. Okay? I gave you the answer. So remember axiom 1, 2, and 3 from Hausdorff. He found it where? Published by Fréchet. And Fréchet got it from where? The question from Adamar was what? To find the écart, or the distance between two functions. And because you are looking at two functions, or the distances on functions, we think about them this way. We look at their value. We have f of x, g of x, and natural, they are real valued, to consider the distance between f of x and g of x. That's the absolute value of f of x minus g of x. And then you do whatever you want with them. Okay? Whether you consider L2 norm, or whether you consider sup norm, whatever. But the ingredient is absolute value of f of x minus g of x. Therefore, the essence for functions is coming from the absolute value between the difference between two numbers on the real line. And using the properties of the absolute value gives me the three axes. You see it now? And if you want to extend it to R2, R3, R4, you use what? The Euclidean distance. Anyway, the point is, okay, we have these three axes. Okay? Axiom number 1 fails. For what? Not for the flower shop. Flower shop is natural. It's just to understand that it's not true. Distance from A to B is the same as distance from B to A. Okay? But even during the time of our friend, what's his name? Fréchet and others, they were looking at two functions. Yeah. So if the two functions, they have a distance equal to 0, they get f and g are equal almost everywhere. They are not equal. So there is a problem. It's really that Lebesgue measure complicated the matter completely. Okay? Now, axiom number 1, axiom number 2, sorry. Axiom number 1, we have a problem. Axiom number 2, we have a problem. Same thing. And finally, axiom number 3, the triangle inequality. Also, we have a problem. Sometimes we have what's known as, we have a constant. Instead of distance less or equal than distance plus distance, we have a number there. Okay? Early on. I'm not talking about fictional. Now, some generalizations are interesting because they answer a problem. Some generalizations are created for the sake of using the ingredient of the proof of the Banach contraction. Try to understand what I'm saying, okay? Please. Some generalizations are trying to understand a problem, and I will tell you one that took me 30 years to answer. With respect to this, I will show you something. Some, you are looking at a fundamental problem, and you're trying to answer that problem. And you couldn't answer the problem within the framework of classical metric. Understand now? So we come up with this what? More general structure to try to understand. That is exactly what Banach did with his Banach contraction plan. Understand? He didn't invent the theorem in terms of tools. He just tried to see something that is more general than the case of what? Functions, the case of what? Sets. Okay? And other examples. But sometimes we have some generalizations that are, they lead to the application of what? Of the tools, iteration, convergence, and so on and so on. Sometimes the problem with this, and this is where I want to come to the work by Professor Hagen, is that sometimes, and this happens to all of us, I'll tell you, papers were published. And I'll explain, because in this course, I will be talking about this. So it's very important about what's known as modular vector space. So The problem is what? When you extend, your brain is programmed to think in terms of what? Metric spaces. Do you understand now? So when you come up with this general structure, you have to disconnect completely from what you learn. For example, to clarify my point, let's say you don't have the triangle inequality. You don't have the triangle inequality. You lose the uniqueness of the limit. Right there. Okay, fine. What if I am not symmetric? Distance from A to B is not the same as distance from B to A, which is natural, by the way. And I'll come back to the flower shop problem. If that's the case, then wait a minute. Like matrices and products of matrices, you have to be careful. What goes to the left? What goes to the right? If that's the case, the limit, now you have a concept of what? Left limit and right limit. So if you don't take yourself out and disconnect your brain from what you learn in the case of classical metric spaces, you will fall into what? Some basic mistakes. This happens to all of us. All of us. No exception. So for example, the module I talked about it yesterday, the module does not satisfy the inequality, the triangle inequality. And I have seen papers published by our group in Thailand, okay? They told them about modular spaces, and they did not pay attention, and they did a theorem, and they published it. And of course, they did not pay attention that they were using ideas from the classical metric spaces in their mind without being careful. You see what I'm trying to say? So this happens to the best among us. So in the work done by Javid, he got some results, and with one assumption, which is valid in the case of what? The metric topology, but is not valid in D metric spaces, according to his definition. Okay? It was not valid. Okay? So this happens. No big deal. Now, why am I talking about this? Not because Professor Javid is here today. No. In fact, I was surprised what his name, Javid, told me. Oh, he's coming. Oh, I was so pleased. Finally meet him. I have been talking about him worldwide. And I really mean it. Worldwide. Name it, I'll tell you where. I mean, everywhere in the world, I was talking about him. So, what happened? My friend, Braley, okay, who is a big name in functional analysis, okay, as well as in fixed point theory, metric fixed point theory. And he came to know about the publication by Professor Javid on D-metric space. And he saw that there is a problem, okay? But it wasn't like, big deal. That's it. It was a problem, okay? And at the same time, a little bit shortly after that, a student from Jordan came to Australia to visit, not to visit, but to study with Braley. And Braley killed him, literally. Okay? And you will see some other examples during the course where you can kill a young mathematician forever. And they will explain to you how. And it's not given to everybody to have the ability to accept a challenge and move on and better yourself. Sometimes when you are young and you hear or something happens to you, it can kill your career completely. So the case of Ziad, he asked him to look at this D-metric space. And finally, they fixed it. Okay? And they came up with a structure that was the essence answering that question. So it was something that he called, I wish he called it D metric spaces. He did not call them D metric spaces. He called them so he called them, as you see here, G metric spaces. Okay? Fine. If I were his advisor, I wouldn't have let him do G metric spaces. I would have said D metric spaces or revised D metric spaces, because that's what it is anyway. So, G metric spaces. Not only they do these G metric spaces, then they went and they proved the theorems, the basic theorems that did not work in the case of D metric structure, but now they work in the G metric space. Okay? So this is the definition. Don't worry about it. Just to show you. This is the definition of what is a G structure. Okay? So it's more general than what? A D structure. Okay? Don't worry about it. Don't worry about it. It's not really. So now, few questions. Very important. That I want you to ask yourself. Okay? And I will explain to you why Ziad was killed. Okay? I'll explain to you in a second. So, number one. I need to find out this structure, because remember what Banach did. Banach contraction principle, he learned from what? Hausdorff book that was circulating, by the way. And he took the structure of metric space, and he took the theorem that was known in different contexts, and he said this is more general. Okay? And then we found some amazing applications of that. You understand? In the case of fitting, and in the case of other structures, okay? Where the tool of metric space became important, took more and more center stage in what? In mathematics. Okay? In this case, they did not offer a motivation or an example that will enrich the structure of a metric. So what did they do then? All of their results are in terms of geometric space. Geometric space. If we have geometric space, if we have this, we have this. We have this, we have this. Theorem 1, Theorem 2, Theorem 100, Theorem 200. You are talking about everybody. Now they took the body of fixed point theory and they try, the body, all of it, and they try to do it in terms of what? Of G structure. Okay? So of course, what happened is Ziad became famous. Why? Because once everybody wants to do and work on geometric spaces, you have to refer to whom? Not to the Hajj. No. You are referring to the guy who gave the definition of what is a geometry. You understand now why is G not revised D? Did you get the subtle message I'm trying to convey to you? Because once you do that, you have to be a little bit sneaky. You have to be a little bit dirty. If you want to stop citing someone, you come up with something, you come up with something. Once you come up with something, everybody will what? Refer to what? To you. So our friend became extremely famous. In fact, in 2016, he was even highly cited. I have the statement here. Let me see if I have it. Yeah, see it? I copied that from a published statement. Now, what's interesting, I told you he was killed by my friend, Rayleigh. He's a really close friend. We worked together. We came up with the handbook of fixed point theory that was written by Rayleigh and my late friend and mentor, Art Kirk. I wrote 2 chapters in that handbook. And it was a handbook of something I was planning to do online. I wanted to have a book online on fixed point theory available, and you can access it online in the 90s, early 90s. So I know very well Rayleigh, very well. We were among the first ones to start what's known as the International Conference on Fixed Point. So I know what kind of mathematics he knows. I know very well. In fact, I will be talking about it this week. There is an open problem, which is still open, whether reflexive Banach spaces, they have the fixed point property for non-expansive mapping. This problem is still open. And what's his name? Alspach gave a counterexample of an example of L1 and the weakly compact L1, capital L1, and the weakly compact convex sets and the non-expansive mapping without fixed point. This is very interesting. I really urge you to look for this paper. I mean, I do have it, by the way, but it's commonly, it's 2 pages. 2 pages in the proceedings of the IMS. 2 pages, 1979, 1980. Huh? These 2 pages, I challenge, as a conjecture, anyone to simplify this example even in 10, 20 pages. Go ahead and explain to us. Number 1. Number 2, can we find simpler example? None, till today. Now, Rayleigh wrote a book on these 2 pages. A book on these 2 pages. I know what Rayleigh knows. Okay? This is not a joke. Wait a minute, Rayleigh. How on earth did you kill GIAN? How? How did you allow GIAN to work only on geometric space? Why you did not teach him more on fixed point theory? The whole fixed point theory for GIAN is geometric. Till today. In fact, I was looking for him yesterday. His work, it's still related to this geometric space. In fact, journals are now not publishing on papers on geometry. So you see the problem where it is. It gives you what? The easiness of publishing, but it limits you in terms of knowledge and what you can do. This is the problem. Everybody will know your name only through your work. They will not know you physically as a good person. They will not. They will only know your work. So my point is, one has to be extremely careful. So to move on this, I got interested into what? Working with someone in France. He just passed away, by the way. And his name is Maurice Pouzet. The last year of my PhD, I visited him in Keynote, and we were looking at the issue of a distance. What is a distance? Who asked this question before? You know the answer. Who asked this question before? Okay, fine. I'm not going to give you a hard time. I gave you a hard time earlier, so now I'm not going to give you a hard time. It was Adamar who asked what? Fréchet to find the distance between what? 2 functions. And I did tell you why. Because 2 functions, this question came after Lebesgue measure theory, and now functions are no longer in the traditional way functions, and therefore you are looking at the distance between 2 sets. So the question does make sense. It wasn't like they knew about the norms, some norms, in the case of continuous functions, L2 and so on and so forth. But he wanted more general case. So the question, in fact, if I rephrase it, was the écart between 2 functions. But if I want to rephrase it, what is the distance? Now we have axiom 1, 2, and 3. No, it's not working. It's not working. Can we find something bigger? Motivation. Motivation. You want motivation? What if I tell you now the work, this work, and this work are close? Oh, okay. Now we have these crazy tools that tells you, oh, 30% similarity, yes or no? And when you publish your paper, they say 30% similarity, 40% similarity. And then you lose your mind, because in mathematics, we use D for distance, X for variable, etc., etc. So the way it is done is completely off. So how am I going to take a poem, another poem, and the two poems are close to each other? Okay, want me to give you better? What about if I take a program and another program and see how close they are? These fundamental questions are still, till today, people are working on them. So when I start working with Maurice on this, it wasn't just for the sake of coming up with what? With a structure that will capture what? The tools by Banach. No. The idea was, let us try to go deeper. Shoke gave an answer. Hausdorff took it over. He gave it to us, and we have it. Let's go beyond that. What would be the distance? 30 years in the making. We just came up with an epsilon answer. 30 years, 3-0, okay? And our paper, when we submitted this paper, it was sent back to us, saying, please, shorten it. It was too big, too big. So let me see if I can. So this is the paper, as you can see there. It came in 2020. And I wanted to pay attention to this one here. So the distance from x to y less than r. Okay? See, this is a relation between x and y. So I'm looking at r as a number, but as a relation. And I say that x, y, the pairs, belongs to r. In your mind, it means this. Of course, not, this is the classical view of the distance. View of now the distance. And of course, we put somewhat conditions. I'll put this, and I want to show you something. Yeah, so here we have all the formal definition under this idea of relations instead of numbers and so on and so forth. Since I want just to show you something here interesting. Okay, now, you see the ball? So remember what I told you. The distance from x to y less than what? R. But now is no longer distance between x and y. It's now a relation, yes? So R is the relation. So you have the ball, but it's a different concept of balls. Now let's go back here. What is the diameter of a set? It's no longer a number. So we have the diameter as being what? A set now. Okay? And of course, we looked at what? Some cases where this structure is more appropriate. It's really interesting, very interesting paper. I urge you to read it if you have time. Don't. Great, so let's move on. And now I get into something serious. Let's move on from the generalized metric and so on and so forth. So now, I want to jump to 1973. In Jamia Islamiyya last year, September 23, as well as here, by the way, I gave them a talk, okay? And the talk was, what was it, Ishaq? Good question? Oh, I forgot, wallahi, I forgot. What was it? Yeah, something like that. Yeah, it was, what is a good question, mathematically speaking? Okay? What is a good question? And what comes to mind is a good question is a hard question. Okay? Earlier today, our friend was talking about Fermat's theorem or Fermat's conjecture, and it's a hard question. Therefore, it's a good question. This is common sense. It's a hard question, therefore, it's a good question. So what I did, I gave them a talk to make them change their mind. A good question may not be a hard question. A good question is once we see the answer of the question. Once we see the answer, then we can see, oh, that was a good question. Or that was a useless question. James came to do his PhD with Kirk. And Kirk asked him a question. Very intriguing question. He told him, can you find? So, first of all, look at the statement I put in. Among the deepest what? Extensions of the Banach interaction principle. The deepest one. And in fact, since I started working in fixed point theory, 1984, till today, I am still puzzled by the work of James Banach. Till today. So it shows you how profound this is. It's not artificial. Now, the question was, listen to this. The question was, can you find a new proof to Banach contraction principle? No. 72. When was the theorem published of Banach? By now you know. 22. 1922, 1972, 50 years. I assure you, without exaggeration, thousands of pages are written on the Banach between this period. No exaggeration. So, how on earth, me, as a PhD advisor, I'm going to ask these new students to find me what? A new proof of Banach action plan. How? Crazy. Why it's crazy? It's crazy. It's a good question or a bad question? It was my essence of my talk. I gave at Jamia Islamiyya as well as here and all over the world. Because I always prepare one talk every 6 months. Was it a good question or a bad question? Don't know. So James, he took the question and starts working on it. Ah, I forgot. Why did Kirk ask him this question? Very important. Forget about James. Why Art asked him this question? You will not find an answer published. You can only find the answer if you sit with Art, have dinner, he drinks, he loves to drink, and then he relaxes, and he's happy, and you ask him this question. You ask him this question. Hey, Art, why did you ask James this question? You understand what I mean? So, my AI assistant will not know the answer. Connect what I was telling you earlier. Okay? So the answer was, he wanted to take a route that was not there. He wanted to find a different route that nobody took. Why? Because the classical routes, thousands of people took it. They chose them. What do you want to find more? Anything you want to think of, they already did it. So finding a different route allows us to look at the problem from a different what? Angle, different what? Direction. Do you understand now? It wasn't just find me a different proof. No, 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 no. It's more to the story than what can be interpreted from the question. Ready? Let me show you what James did. Okay? Okay. So this is James. Okay? He started by looking at this. Now, why? You are not going to find the answer anyway. The AI assistant will not know. Period. Why? Why did James start like this? Why? Okay. The answer is, if you go back to the proof of the Banach contraction principle, what does it say? The classical proof. I'm talking about whether it's Banach or the one before, known to our friend, what's his name? Picard or Liouville or whatever. It doesn't matter. How? And I did tell you earlier today. What do? Input, output, and what? You iterate. You loop it. Yes or no? So the problem of the fixed point is where? Is only by looking at what? At a point. You start what? Looping. You start what? Iterating, and then hoping what? That it will go where? To the fixed point. You understand now? So we are just looking at what? At the orbit. Just x, t of x, t squared of x, etc., etc. Do you understand now why he was looking at t squared and tx? Otherwise, it doesn't make sense. Let's continue. He added this term here, this term here. Yeah? No problem. Then, he moved this one to the other side, and this one to this side. You will find 1 minus k times dx dx, and here you will find this minus this. Divide by 1 minus k is less than 1, and you end up having this inequality. Yes? Are we okay? How many steps? Huh? How many steps? 2, 3, to be generous? Huh? No big deal. So, is the question hard or easy? I just told you, hard question that nobody can answer. Oh, it's a good question. What kind of question is this? That you are using something as simple as this. Yes or no? Shall we continue? Let's continue. I want you to pay attention to this. What's this? This is a function of x. Why did I say x, not tx? Because if I replace x, this one, do you see it? It's the same function here of x, here of tx. Therefore, what do you have here? You have a function of x minus a function of x minus a function of tx. Okay. Let's move on. You see it? So I have the distance from x to tx less or equal than phi of x minus phi of tx. Let's try to understand this. Now, let me take you a little bit down to understand this business. First of all, do you see phi of x minus phi of greater than the distance from x to tx? Therefore, it has to be positive because the distance is positive. Yes or no? Therefore, phi of x is greater than what? Phi of t of x. Okay, let's look at phi as the level of energy. So you take a particle, you excite it, magnetic field or electrical field, it starts to get excited, and then when it's excited, it moves to the next layer. But the effect is to lower your level of what? Of energy. Do we agree on this? Do you see it? So, why? Because if you don't see it this way, you will not understand what electrons are. So try to follow me now. So you take a particle, you excite it. The effect of the excitement, experiment. Then it moves, but it moves to a layer with lower energy. Yeah? So far so good? What happened when you reach the lowest layer of energy? Wait, follow me. Huh? What is the function? What's the function? Function is 1 over 1 minus k, distance from x to tx. Yes? K is less than 1. Therefore, this function is what? What can you tell me about this function? This function. Because this is phi of x. What can you tell me about this function? Very important. What can you tell me about this function? Positive. Yes or no? Huh. So if the function is positive, which is the energy. If the function is positive, and you are lowering what? The level of energy. What happens if you keep doing it? What happens if you keep lowering what? The level of energy. Okay? If you're lucky, and you reach what? Because you are positive. Therefore, you reach what? No, that will be ideal. Ideal to get to the level 0. But let's assume we reach the lowest level of what? Of energy. In fact, that's what happens. You will never reach what? Level 0 because you don't lose energy. Okay? So you just get to the lowest level of energy. Lowest level. Okay, we are mathematicians. What does that mean? The infimum. Function is what? Positive. I have an infimum. Go down, closer to the infimum, till you reach the infimum. I assume you reach the infimum. What happened to you when you are at the infimum? And you excite again the particle. Where is it going to go? Nowhere. Because you are at the minimum of the energy. Oh. What happened? Now, I'm exciting the particle. I am at the lowest level. Yeah? I know that this one, once I excited the particle, this level of energy will be less than this one. But you are at the infimum. Therefore, what happened? This one and this one are what? Same. Because you cannot go below the lowest level of energy. But if they are the same, what happened? What happened if this is the same? What happened? This will become what? 0. And if this is equal to 0, what happened? So your particle doesn't move. It stays exactly what it is. Okay, in our fancy wording, T of x equal x means what? You got the idea? Now, in general, fine. So here you see it. Positive. It doesn't have to be positive. But I need to be what? No. I need to have what? Some lower what? Because otherwise, if I'm not careful, and they keep going down, I will go where? Minus infinity. I don't want to go to minus infinity. And therefore, I just need what? To be bounded what? So let's say you are bigger than C. Yeah? Yeah? You are bigger than C. What happens if you take phi minus C? This problem is invariant. Whether you are taking phi minus C. The problem is invariant. Yes or no? There's going to be phi minus C here, phi minus C here, minus C plus C. C is gone. Therefore, assuming that phi is 1, or bounded below is exactly the same. Do you agree on this? Okay, number 1. I'm taking you into the mind of what? Of characteristic. It gets complicated. What if I take T of x equal x? What's the name of this? Huh? No. Everywhere. T of x equal x. What's the name? Thank you. Identity map. Yes? Huh? T of x equal x. What happened to my inequality? Huh? So, quality is what? T of x equal x, what do I get here? T of x equal x, what do I get here? Therefore, your T satisfied. Now, what's the problem? What did I tell you? question was to find what? What Kirk asked James? Find another proof to what? By playing, he came up a few steps to this problem that you see on the screen. And then he said, wait a minute, T equal identity satisfied. But guess what? T equal identity fails the Banach contraction principle. Why? Because it's not a contraction, and we don't have uniqueness of the fixed point. Everything is fixed. What does it mean? Did he fail? Did he abandon? No. He just discovered a new class of mapping. Contractions are one of them, but not only contractions. You see now? But the question is now, changed. Changed. What's the question now? Do we have a fixed point? So it's no longer, he knows, it's not going to be Banach contraction. Oh, it's gone. It's more general than what? Banach contraction principle. Question is, do we have a fixed point? Now, wallahi, I told you, this problem of Karisti and the paper that came up in '76, till today, I am puzzled by some of the facets of this data. Till today, we're talking about almost 50 years. Yeah, 50 years, because it was '74 when it was submitted. Now, let's start with the orbit. Let's take a map. I called it C. I am the one who called them C. A long time ago, by the way. Why? You know why. Class C. You know why. Christy. So by respect to his work, I didn't call them K, Khamsi. No. C, class. So let's start with X. Ready? Are you with me? Let's start with T of X. We have that. What about T squared of X? Then what happens? What you're going to find is, fine, T squared of X is less than 5 T of X, less than 3 of X. So the level of energy now is going down. Yes? And because D satisfies the triangular inequality, you have also the distance from T from X to T squared less or equal than. Okay. Now, let's continue. Continue. What happened to the sequence Xn, which is the orbit? We can easily show that it is Cauchy. Triangular inequality and the equality you see there. We can show it's the famous telescoping series. Remember this from calculus? It's Cauchy. Therefore, it's Cauchy. Therefore, why does it converge? It converges because, good job. So number one, I need phi to be bounded what? Below? Good job. Number one. Number two, I need the metric space to be what? Complete. Good for you. Now, are we assuming some weird assumptions? No. No. Why? Because what is the Banach contraction principle? The metric space is complete. Is a contraction. You have a fixed point. Yes or no? So we're not coming up with some weird assumption. No. Great. So now we take what? The orbit. It's Cauchy. Therefore, it's convergent. Because I'm assuming what? Completeness. What happens to the limit? In the case of what? Banach, the limit is a fixed point. Why? Because T is continuous. You understand? We use the fact T is Lefschetzian, is continuous, we're done. What happened here? I built an example, James, that T may not be what? And it satisfies that. So in his class, this new class of mapping, not necessarily you are continuous. If you are not continuous, the limit may not be what? Point. Now, James throws the towel. Yeah. He got stuck. He reaches what? Omega. And he said, what can I do? He knew that T may not be what? Continuous. And therefore, he did not know what to do. Lucky him. He was a student of whom? Here. And what is famous about here? He uses transfinite orbit like bread and butter. Like here, if you want, rice. It is tool of daily research. James did not know that. I did not know that. I learned it from here. So, what does it mean? This is very interesting for you because you don't like ordinals, and it's a big mistake. So, look what happened. Start with x. X0 here. X1, which is T of x. X2, it's n. Omega, this is converged. Okay? If everything is good, which is the case here, that omega may not be fixed. Okay, fine. Let's take what? Continue. T of omega. And then what? T squared of omega. So that's using what's known as transfinite what? Orbit. We are going beyond the first countable, the classical orbit. We're going beyond the classical orbit. Okay, if you keep going, this function phi keeps going down. You see, this phi with the orbit, transfinite orbit, keeps going down. Guess what? It's a property of the real numbers. You cannot keep going down forever. If you have, with every ordinal, you cannot exceed the cardinality of. So now we are getting into something that James did not know. It was what? Kirk who helped him out. He said, okay, don't worry, I know what to do. We can keep going. If you go to my book, and I know that the book was sent to you by Javid, if you go to the end of that book with Kirk, if you look at the end, we put an appendix that discusses this, what I'm talking about. On the real line, you cannot have increasing or decreasing numbers with indexes from all ordinals. They have to what? Eventually what? Become constant. They have to stop. They have to saturate. What does it mean that there is an x alpha equal to x alpha plus equal to all of them? But x alpha plus is what? T of x alpha. Therefore, what happens? X alpha equal T of x alpha. Therefore, we reach what? In order to do this, to keep going, you need one more assumption. It's in the proof, but one more assumption, which is what? That this function phi is lower semi-continuous. I can show you the technicalities, but as I told you, don't. Think about it, and you can read it and understand what I'm talking about. So you need the lower semi-continuity to keep going. Number one, if I take an orbit, normal, countable one, it's Cauchy. I need to converge. If I need to converge, I need to assume that MD is what? Complete. What else do I need? Phi, not to go to minus infinity. Therefore, I need phi to be what? Bounded below, okay? And I told you whether you assume bounded below or positive is the same. Great. And what else? You need phi to be lower semi-continuous for this orbit to be transfinite and keep going. You have fixed point. Period. Oh, I'm sorry. Oh. Why? Why did you go that fast? Oh. Okay. So do you see it now? And D is what? Complete. Function phi is positive, bounded below. lower semi-continuous. T satisfies this condition C. Therefore, T has one. Do we have one? No. Identity will work. So you don't have one. Do I have the fixed point after countable iteration? No. You may have to go beyond countable iteration. Oh, no, wait. I love when my students, they take it for granted. I told you I'm still till today pondering on this theorem, puzzled by this. What did they tell you? What was the question from art? So always, and you are going to be seeing this for the next 4 or 5 days, I want you always to go and think what? I will say it every day. Think what? Outside of what? Don't be like the AI, my AI assistant, who only thinks inside the box. I want you to think beyond the box. What was the question from art? It was find another proof of the Banach contraction principle. Look where he is now. Do you understand the essence of the question? This is what I'm trying to tell you. The essence of the question. The essence of the question was what? Can we find a different route that can teach us something what? Different. Oh, by the way, the energy explanation I gave you, that was not art or James. No. So you see now, we have a new what? A new window. A new window that nobody saw before. Why? Because they went the traditional way. They went the route that was everybody took. By taking this different route, they saw, like for example, what they say, the tree or trees that hide what behind it? The forest. So the paper was what? They looked for an example. And this connects what? Let me just tell you, without going to details, I didn't put it right here. This condition connects x with tx. Why does it fail continuity? Why? Because it doesn't tell you what's going on between x and y. Continuity means x close to y. T of x close to what? T of y. But here, you only have a relation between what? X and tx. How? There is no way you are going to be able, from this condition, to tell me that if x is close to y, t of x is close to ty. No way. Anything that connects x and tx, that's maybe what? A tool to use. This category of mappings, we call them inward mappings. Inward mappings are mappings that connects x with tx. Without going to details, I didn't put it because that wasn't the purpose. I want to convey another message, that's why. I didn't want, you can find it. So he published this theorem, 2 more papers on inward, defended his PhD, and after that he became a cowboy for years in Texas. Why is that? It's amazing what he discovered. Why he became a cowboy. Now, all what I said is here. All what I explained to you is written here. And this PDF file, they have it, as well as my lecture notes. Okay? The whole course is based on this lecture note that I was writing just before coming. They have it as well. It's there. Okay. So let's continue. Now, that was, I said, 1974. Published in 1976. Okay? At the same time, 1974, Eklund published a paper. And he published this theorem. Do you see the reference? Yes? 1974. Évaré-Clonde was my master thesis advisor. Okay? At École Polytechnique, when I did my senior thesis, I did it with him, with Évaré-Clonde. So I know very well Évaré-Clonde. Okay? So he's not like somebody I'm going to trash or somebody I'm going to say something bad about him. No, he was my advisor. Okay? And he was a wonderful person. In fact, he's a wonderful person. There is more to the story about him in France and so on and so forth, and how he behaves with Muslims and so on and so forth. But that's not, I'm not talking about him being a good man or a bad man. I'm only talking about what? Math. In mathematics, we don't have this feeling, emotions. Oh, you are a good man, therefore. No, wait. Mathematics is one thing. You are a good man is something else. Yes? Huh? I can tell you you are wrong, mathematically speaking, and I can love you for the sake of. Yes? No problem. Now, to publish this, look at this statement. Now, what do you see in common? You see a complete metric space, yes or no? And you see the function phi, which is what? And it is what? Also positive. Yes or no? But there is no fixed point. Yes or no? There is no fixed point. So, on Caristi's paper, the conclusion is a fixed point theorem. On Éclonde's paper, it's nothing, there is no fixed point. Now, I want you to pay attention to something that you did not see. So I'm going to give you a few seconds. Ponder on the reference of Éclonde. Okay? Ponder on the reference of the paper by Éclonde. Okay? Do you see something? Tell me. Something that got your attention. Anyone? So, I mean, in fact, one question per day. Huh? I already gave you hard time earlier today. I'm not going to give you a hard time now. Okay? So let's move on. How many pages is that paper? How many pages? Huh? How many pages? Look, there you have it. 324 to 3 what? 53. So almost what? 50 pages. Now, I swear, this paper is one of the most beautiful papers ever. Now, what is special about that paper is what he discovered. The application. Okay, wait. Let's go back to Caristi. What did we say that Caristi did? With his theorem. He only did what? You remember the technical name? Inward mapping. And that's it. This guy, he blew it. In fact, to a point where in this university, one of your faculty came up with a journal dedicated to this theorem. This theorem. Conference in 2023 here at Aligarh was entirely dedicated to this theorem. This theorem has now school worldwide. This theorem. Not Caristi. This theorem. Why, Amine, are you insisting on connecting the two? Why? Why are you talking about Caristi and Éclonde? Why are you insisting? Okay, if you go back to Caristi paper, you will see in the Caristi paper when it was submitted. But if you go back to this, you don't see when. Let's move on. I still have something for you. That's why he became a cowboy. Now, to understand all this, both. Oh, by the way, here are, I just did this yesterday, by the way. Okay? So it gives you an idea. Look at the first one. The first one is a book, by the way. Okay? And for your information, Tamam is one of the biggest mathematicians, applied mathematicians in France. Okay? So if you look at the book is what? 7,000 what? Citations. And listen, this is not about some playing with citations. No means, none whatsoever. These are real citations to real mathematics. Okay? Look at, these are the top ones for Eklund, the top ones. So look at this one. This one, this is the famous one, huh? The one I just showed you, yeah? Huh? 3,104 citations. Okay? And then problem variationnel, another one, and non-convex mathematics. All of his work, and this guy has done tremendous work. I mean, on economics and on tremendous body of work. I'm talking about Eklund, okay? But you see, the top ones are all related to what? To the variation of what? The theorem I just showed you. Okay? So it showed you the importance of that theorem. Now, of course, if I show you this theorem, it means nothing to you. Let me make it now baby for you. Ready? First, if you look at it, it means, wow. Let me make it for you piece of cake. Okay? Why? Because once you understand it from a piece of cake point of view, you will understand what's going on between what? James and Eklund. You understand now? Let's do it. Ready? Oh, these are the applications of that theorem. Profound applications, not inward mapping. Let's move on. Now, what did they write in red? That this theorem, Karisti, as well as Eklund, especially Karisti theorem, for me, I spent so many years working, so many years. I did not publish within 2 weeks. I did not publish within a month. Years working on this theorem. And what did they put there? Still, I am puzzled by some of the sides of Karisti's theorem. Okay? So, what is behind both Eklund and Karisti? Eklund saw it. Karisti did not see it. That's fine. What did they see? He saw something that was popular by Brownsted. But it wasn't Brownsted. The first one who used that tool was Bishop and Phelps in that paper, 1963. But the one who got the tool out from that paper, 63, and made it popular is Bishop. Because of that, this tool now bears the name of Bishop. Understand? It's originally where? In Bishop and Phelps paper. Okay? You will understand. Don't worry about it. It's a very simple tool. It's not like something fancy. No, just give me a second. Ready? Let me show you the tool. Here it is. So what do we have? Do you see the connection now? We have what? We have what? Metric space, yes? We have function what? What? 0 plus infinity. So we have what? Same stuff used by Karisti and Eklund. Yes or no? Same. Forget about the assumption, completeness, and lower to continuity. But what you have in your hand, both of them are using it. Metric space and this function phi. Now, this order has a name. What do we call it? What do we call it? What do we call it? I swear I didn't hear you. No. Brownsted order. We call it Brownsted order. Who discovered it and used it? Bishop and Phelps. 63. Who made it more in applied analysis and so on and so forth? Brownsted. So now look at this. X less or equal than y. If and only if we have this. So this inequality that is of metric nature becomes now discrete in me. You need this. So now we are no longer what? We're no longer talking about what? About metric business. We're talking about discrete. We're going to discrete set now. Go back to Kirk. What did Kirk ask James? You know, he told him, please try to find another proof to what? Banach contraction principle. Look at this window or the door that James opened. Hey, why aren't you talking about Econ? I'll tell you in a second. Give me a second. So he opened the door. He opened the door. Look now where we are. We're talking about what? Looking at this problem from a discrete point of view. We're no longer looking at the problem from what? From a continuum point of view. Let's take now, by the way, it is a partial order. So I'll leave it to you to show that you cannot have x less than y, y less than x, because this will give you what? Phi minus y minus phi of x, phi of x minus phi of y, or 0 is going to be negative, and therefore it's equal to 0, therefore x is equal to 1. Okay? So you have the anti-symmetry, and you have the transitivity because x less than y, y less than z, x less than z because of the triangle inequality. Okay? As long as d is additive because of the triangle inequality, you get a partial order. So it's a partial order. Okay, fine. Now, we have an order. Now we have to think in discrete set theory. Forget about what? Functional analysis. You are here now. You have to go back to your classes in discrete sets. Okay? What do we have in discrete sets? We have the concept of minimum, infimum, supremum, maximum. But you may not think of it like, for example, the set of subsets n. Yes? What's the minimum? Empty set for the inclusion. And what's the maximum? N, the entire set. But what if I remove the empty? What happens? I remove the empty set. What happens? You have what's known as minimal. So singleton will not be the minimum, but there will be what's known as minimal point. Meaning what? Nothing below them. Yes or no? And the same goes for what? Maximum point. Are you with me now? Discrete set. You teach this to any student, senior math student. When do we have a minimal point or maximum? Yalla, please, tell me. Yalla. When do we have minimal point or maximum point? When? One word. Two words, but that's good. Good job. Yeah, zone. Yeah. Zone is the tool that tells you you have what? A minimal or maximum. Okay, how? What are the assumptions of zone lemma? If you have a totally ordered chain, okay? Chain. You have what? A lower bound. You have minimal. Or if you say any chain, totally ordered chain, you have what? An upper bound, you have a maximum. That's zone lemma. Yes? Are we okay? No problem? Do we need zone lemma to have minimal and maximum? No. Let's take two trees. And by the way, they call them trees. Okay? Two trees. One has a root, one does not have a root. Are you with me? Basically, if you want, they call them trees, by the way, in discrete sets, and forests. Let's call it, for us, two subsets. One is totally ordered, with no minimum, no lower, no upper. An infinite like R. And the other one has root, in other words, minimum. Are we in? Okay. This minimum is minimum. And by the way, they are not connected. In other words, they are not comparable elements. Any element in this tree is not compared to this element. Okay? So only these ones are comparable, and these ones are comparable. This element, the root here, is a minimal point. But you see, this set of these two trees fails Zorn lemma. Why? Because of this one. You have a chain, but you don't have a lower bound. So Zorn is too strong to give you what? Minimal point, maximal point. But you may have minimal and maximal without having what? All the chains having lower bound or upper bound. Are we in? Okay. So now let's say this. Sorry. Let's look at now minimal. So this definition of minimal. X tilde is minimal. Anything below it is equal to it. Yes? That's the definition. Now look at the theorem next. Now you will understand. It's nothing. Yes or no? I'm not showing you something fancy. Yeah? You agree with me? Huh? Any student who took a little bit of math knows what I just said about discrete and partial order. Yes? Huh? Okay. So now let's continue. And I will stop there anyway. Oh. Yeah. Okay. Pay attention now. Now let me show you how baby it is now. Everything comes collapsing. Ready? So we have Brownsted order. This is Brownsted order, yes? You remember definition, yes? Huh? And look at now. Look at T. I want to show you something. Look at T. T goes from N to M. A map. Such that T of X is less than X. For the Brownsted order. If X tilde is a minimal element, T of X tilde is less than X tilde. Therefore, T of X tilde equal X tilde. Meaning what? That minimal is fixed point of T. Yes? Therefore, what's that? That's carries T. Yes or no? Shall we continue? So, first part 1. That's carries T. So remember, you have to remember, what does it mean then? This means the distance from X to Tx is less or equal than phi of X minus phi of Tx. You remember the Brownsted order. Let's go to 2 now. Ready for 2? 2. Let's take X, which is different from the minimal. You cannot be below it if you are different. You cannot be below. What does it mean, not below X tilde? But it means exactly what you have here. That's a clone. But a clone has an epsilon. Has an epsilon here. But guess what? The whole theory, instead of working with D, I can work with epsilon D. It doesn't matter. If I multiply the distance by an epsilon, the whole assumptions are the same. Completeness, everything, continuity, because you are multiplying by a number. And therefore, to have it D, or to have it with epsilon times D, epsilon is fixed. It's the same. Makes no difference. Now, statement 1, carries T. Statement 2, echelon. Oh, wait. Don't think. Oh. Wait. What was X tilde? Tell me again about it. Look at it in the theorem. What is X tilde? It's a minimal of what? Of the Brownsted order. So it's the same element in the conclusion of what? Carries T? Same element in the conclusion of what? Oh, maybe there is something there. So who is the first one? Are they at the same time, independent of each other, or not? It happens to be not. Our friend Echelon, my good advisor, got access to the paper by Keynote. Once he got access of the paper by Keynote, he saw the profoundness of the work done by Khamsi. Now, when he published his paper, there is nowhere to be seen the ideas of what? Aristotle. Because the ideas of Aristotle are all based on a map. His work is totally different. What happened to Aristotle? Yeah, he gave up. Why he did not give him what? Credit. He was so disgusted that he went to his farm in Texas and he became a cowboy. Now, what if Ivan decided to say that he got the idea from Aristotle, which would not take anything from his work, because his work is so profound that it could have been just giving him what? Credit. But he didn't do it. What's the lesson from it? Big names are not to be trusted as being above our human behavior. They can also be nasty and kind. Let's maybe conclude here. I'm going to conclude. How do we get the minimal point? I will conclude here. How do we get the minimal point? You just told me. Huh? By zone. Yes? If we have zone, we have minimal point. Guess what? We have zone if and only if we have it. You see this here? We have zone if we assume complete matrix space and phi lower symmetry. So the main assumption in Khamsi and in Echelon, they gave me what? Zone lemma, therefore minimal point, therefore the conclusion I just told you. But wait, and I will leave you with this. I just told you, remember the trees. You don't need zone lemma to have what? Minimal. Meaning what? That maybe the assumptions, completeness, and lower somatic continuity are not optimal. What are these optimal? Till today, nobody knows. Thank you very much. No. How are you, Zahar? It's okay. We don't care.
Okay, no problem. No issue.
And are we meeting tonight? Yeah.
Yes.
Yeah, let's meet. Join you guys.
Yeah.
That's fine.
But I think yesterday dinner was okay. That was not so much.
Soup was bad.
Huh?
Soup was bad. Chicken was good.
Chicken was good, but soup was
no.
Yes,
I
your
just
phone?
reading. Yeah.
Oh. इसको बहुत बड़ी कंपनी है.
Walaikum salam.
Yeah, Mike, I think you should
Oh, I'm
remember.
sorry. Yes. I'm sorry. T is contractive if this inequality is satisfied for all distinct xy. So there is a well-known theorem for this. First of all, this example shows that basically every contraction mapping is contractive. So this is the counter example. This example shows that this is a contractive map which is not contraction map. So next one. This is the one of important property of contractive mapping on metric space. This is that if a contraction mapping has a fixed point, then it must be unique. And proof is very simple. If we consider if possible, there are two fixed points of a contractive mapping T. This is contractive mapping, and there are two distinct points, fixed point. Then we apply the contraction condition on these points. So we find that d Tx Ty equals to d xy. Now as T is a fixed point, therefore this is equals to Tx equals to x, and there also y is a fixed point. So this is a contradiction because both are non-zero, because x and y are distinct. So if a contractive mapping has a fixed point, then it must be unique. And there are some facts about the motivation of L-distinct fixed point theorem, because we cannot extend Banach contraction principle directly to contractive mapping, because in contraction condition k to the power n has an important role. Whenever we prove that the sequence of Picard iteration is Cauchy sequence, then it helps us, that is k tends to 0. But in case of contractive mapping, this does not hold. So this is an example. Where metric is complete, and this is an contractive mapping, but there is no fixed point. So in this direction, independently two mathematicians, Nemetsky and L-distinct, both proved an important result, which is called L-distinct fixed point theorem, or Nemetsky L-distinct fixed point theorem, and this is that result. Every contractive mapping on compact metric space has a unique fixed point. Moreover, this fixed point is obtained by the Picard iteration, means that any sequence of Picard iteration converge to this fixed point. So but here is this problem, because we have, this is our contraction mapping, which has a fixed point on complete metric space, and here this is our contractive mapping. And we know that every compact metric space is complete. So this is our compact metric space. So for this mapping, this mapping has a fixed point on complete metric space, and this mapping has a fixed point in this class of metric space, means that compact metric space. So there are many generalization of contractivity condition, but our aim is to focus on those contractivity condition which lies between here, means that between contractive and contraction. Of course, all these covers this also, but they admit a fixed point on where complete metric space. So Picard operator means that if T is a self-mapping on a metric space X and it has a fixed point or fixed point set is non-empty, singleton, means that there is a only unique fixed point. Then T is called a Picard operator if for every X in X the sequence of Picard iteration. This sequence is called Picard iteration with initial point at X. This converges to always this fixed point. These operators are called Picard operators in the sense of Russ. So there are so many contractions which lies between in this class 5 contractions, and there are so many results which are Picard operator on complete metric space, and besides this F contraction is also lies between in this class, and Mir killer, which is a well-known contraction, is also lies between this class. So first of all, we discuss phi contraction, which is more natural. Basically, motivation of phi contraction is that if we consider contraction inequality, means that usual contraction condition d tx ty. This is less than equals to k time dxy, and here k lies between 0 to 1. So we know that the range of d is r plus means set of non-negative real numbers. So here we multiplied k with a non-negative number k time t, where t belongs to r plus. So this also belongs to where if k lies between 0 to 1 and t is a non-zero real number basically, then t also non-zero real number. Okay, so we can extend this idea kt, product of these two numbers, by using a map. So if we consider this is equals to phi t, this means that phi operate on an element of r plus, and this goes to r plus. So phi mapping is from 0 to infinity or r plus to 0 to infinity. First thing is that, so we can replace this condition, of course generalize this condition by considering this map. dtx ty less than equals to phi operated on dxy, and one condition is deduced from this contraction constant also. We know that as k is less than 1, this means that kt is less than t, because t is a non-negative real number. Okay. So we deduce this property from here. So motivation of the phi contraction is that we can replace the contraction condition by this map. It is positive, yes. R plus sorry, yes, yes, yes. This is only satisfied for T is positive. Okay. So a mapping from here to here is called control function. Is called control function if it satisfies this inequality for all non-zero T. Okay. And if phi is a control function, then this inequality is called phi contraction. So under this restriction, phi t equals to kt, this reduces to usual contraction condition. So there are another examples. This is an important conclusion. That is, every phi contraction map is contractive. So proof is very easy. If we consider two distinct points x, y in X, then dxy is non-zero, means that this is strictly positive. So we can apply the phi contraction condition here, d tx dy less than equals to phi dxy, and as it is strictly positive, so we use the previous condition of control function, we get dxy. So all classes of phi contractions, whether it was Boyd-Wong type or Matkowski type or another type, they lies between contraction and contractive mapping, means that every phi contraction is contractive. No, different. There are so many theorems depending on phi contraction, but most natural result is this is an example of, this is one of the class of control function where phi is monotonically increasing and this sequence is converges. So automatically using these two conditions we prove that phi is control function, because the proof of corresponding theorem is very easy and we naturally prove this theorem directly. And in Boyd-Wong theorem there are another two conditions because this one, because phi is increasing here, so we can deduce phi is control function, And when we prove that the sequence of Picard iteration is Cauchy, then it is easy to using condition second. But it fails in the context of Boyd-Wong theorem, because Boyd-Wong theorem we prove Cauchy sequence by contradiction method. This is the well-known result of Bianchini-Grandolfi, and here every phi contraction mapping where phi is a strong comparison function defined on a complete metric space has a unique fixed point. Also, this forms a Picard operator. And now we generalize condition second, which is generalized by Matkowski. Instead of convergence of series to 0, here they consider this sequence phi to the power n t. This tends to 0 whenever n tending to infinity. So here, therefore, every comparison function is a control function we can deduce from here. It is easy. So this is one example, which is a comparison function, but not a strongly comparison function. And Matkowski proved a fixed point theorem under phi contraction for this class. This is the main result of Matkowski. Let XD be a complete metric space if phi is a comparison function such that T is phi contraction. Then he has a unique fixed point. And therefore, this conclusion is directly hold. Every contraction is BG type contraction, and this implies this is a Matkowski contraction, and reverse implication need not be true in view of foregoing example. Okay. Now, instead of monotonicity, because in both theorem we assume that phi is monotonically increasing. If we wish to remove the monotonicity requirement, then we need continuity requirement. So simultaneously of first result, Browder proved such type of result. But in the theorem of Browder, there was an extra condition. So after removing this condition, Boyd-Wong proved an important result on phi contraction. So these are some basic notions: right continuity or upper semi-continuity, and merging both of two types continuity, we find another class of semi-continuity. This is upper semi-continuity and right upper semi-continuity. Now this theorem is very important because in Matkowski theorem and another theorem, both theorem involve a classical method of proof. In these two theorems, we show that Tnx means that sequence of Picard iteration is Cauchy directly, likewise in the proof of Banach contraction principle. But here this is not possible. So in the proof of Boyd-Wong theorem and another theorem associated with this result, we used Cauchyness by contradiction method. Of course, in that theorem we find that this limit dxn xn plus 1 equals to 0, but it does not imply that xn is Cauchy always. So sometimes some authors called such a sequence asymptotically regular Cauchy sequence, and some another authors Unisi said that this this is called semi-Cauchy sequence. So here we directly prove that in Boyd-Wong theorem this condition holds. This means that sequence of Picard iteration is semi-Cauchy. And by contradiction method, then we show that Xn is Cauchy. So this is result only two condition on phi in Boyd-Wong theorem. First is phi is control function, and second one is continuity requirement, and this is right upper semi-continuous. Only this condition is enough, and many results becomes consequences of this result, because if we consider natural version, means that phi is a continuous and control function, then automatically deduce from this theorem, Boyd-Wong theorem. And one more theorem is proved by Mukherjee. He considered phi is right continuous. So his theorem is also consequence of this. So there are two directions. This means that there are two directions in phi contraction. One direction, in one direction, phi is assumed to be monotonically increasing, and some another one condition regarding convergence of series or convergence of sequence of iterate of phi. And second direction is continuity requirement, for which this theorem is holding. And these are counter examples, because Matkowski theorem, basically Matkowski theorem is generalization of first theorem, but Matkowski theorem and Boyd-Wong both are independent. So this is one example where phi is not comparison function, but phi is Boyd-Wong type function, means that right upper semi-continuous and control function. And this is example from Javid paper, and this example from Matkowski original paper, where phi is comparison function, but not Boyd-Wong type function. Several authors said that Matkowski theorem is generalization of Boyd-Wong, but it is wrong, because these two examples are available in literature. This is the generalization of another generalization of Banach contraction principle, and motivation of this is that this is our Banach contraction condition. If we take lambda equals to 1 minus k, this means that lambda lies between 0 to 1, and 1 is included here but not 0. So from this we get k equals to 1 minus lambda. So if you put this value is here, then this becomes dtx ty less than equals to d xy minus lambda time dxy. Here, so yes, lambda. No, thank you. So this is again replaced by an appropriate map psi, and this becomes weak contraction, generalizing this idea. So this is your this is our weak contraction. Jameski shows many equivalent condition on contraction mapping. So under certain set of plane means x square, subset of x square, means that a domain of metric. So these two conditions are equivalent, Boyd-Wong and weak phi contraction, or under some additional assumption, this is equivalent to Metkoski contraction. Because we use identity minus psi equals to phi, identity mapping on R plus minus psi equals to phi, and using the properties of each other, we can connect both these two type contractions. So here lower semi-continuity, idea of lower semi-continuity is used, and these are two conditions only. Basically, in original paper of Rhodes proved this theorem, weak contraction principle. So Rhodes use several other conditions, but later on it is proved that only these two conditions are suffice. So if psi belongs to this class, then the weak contraction defined on complete metric space has a unique fixed point. Lastly, we discuss one of the important of novel class of contraction due to Twardowski, which is called F contraction or tau F contraction, because it is depending on a positive constant tau and a mapping phi from positive real numbers, non-negative set of non-negative set of positive real numbers, 0 plus 0 infinity to 0 infinity. So these are three conditions which are imposed by Twardowski. Later on, many authors discuss all these conditions, and capital F from capital F from 0 infinity to 0 infinity. Here 0 is not included, 0 infinity to 0 infinity. Yes. Oh. Here 0 is not included, likewise Boyd-Wong contraction or Metkoski contraction. Yes, diverge. These three conditions are considered by Twardowski. So later on, Popescu and Stein observed that F2 and F3 can be removed from Twardowski result, and also phi is strictly increasing. This condition can be weakened by phi is increasing. So this is one of the most important generalization of F contraction. So we call this theorem Twardowski-Popescu-Stein theorem. Let XD be a metric space and F is a function, real valued function on, this is real valued function. Real valued function defined on 0 plus 0 infinity, and operator on compact between them, which is proved by some recent researcher and that was first contraction series. Matkowski contraction is CJM contraction. And Boyd-Wong contraction is Meir-Killer contraction. And also CJM, Meir-Killer contraction is also CJM contraction. And F contraction is also CJM contraction. Therefore, CJM contraction is a large class which contraction and contractive map, and it has a unique fixed point on complete metric space. So, under some additional condition, F becomes Matkowski contraction, and under another some additional condition, F contraction becomes Boyd-Wong contraction. But overall, F contraction is independent from Boyd-Wong and Matkowski. Yes, 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 yes. But additionally, some assumptions. I think F is right continuous. Yes, yes.
Thank you, Aftab. Of this talk. So we have a complete meeting space, and we have a whole set of contractions. Okay. So if you take any contraction on a complete space, we have a unique system. Maybe we have a maybe what is the problem? So this was I could say maybe my opinion. Okay. And this is the my last information. If I take any element from here, suppose from this okay, unit. The question was that if we extend this class, so this is a very natural question because we want to prove the problem or solve the problem for more general. So that's why we want to extend this class. So suppose this is my class contract or this is contract. So this is basically bigger class. But when we take any element from this class, we don't have any guarantee of a fixed point on the complete. So for that we have to reduce our space. So like here and this here. So this is basically compact meter. So on one side we are basically enlarging our class of F, other side basically our space is basically reduced. The question is that if I want to basically I want to remain basically my space same complete, but I want to enlarge this class. So basically in all the jitne bhi representation se basically all the author basically extend this class like contractions, for example nonlinear, then with more, Aligarh, more, and CJM like this. So suppose this is basically my now final class. So still we have some gap in this class. So maybe we can think about for this one. So maybe there is some gap here. So we have again fixed point on this complete meter. So this will extend the class up to for the contraction. Because all are the basically generalization of a contraction. And all have a basically fixed point complete meeting space. So again we have a gap here in this part. So we need to think about some new operator. So we can basically the fixed point on the complete meeting. So this is a very nice maybe expression for this. So this was the basically whole idea of these contractions. We are just extending a class of operators and we are trying to find out the fixed point over complete meeting. So still we have some gap. So thank you very much. So yes, of course. No, but because applicability is basically goes to all the bigger space. No, I'm talking about the reverse case, like where A contracts, A contracts with two contracts. Because there is compact with complete.
Yes, yes. There are some many classes. No. Yes. Look. Yes. Pre-compact metric space. Yes. There are 4 or 5 classes which lies between compact metric space and complete metric space, where this contractive mapping has a unique fixed point, which is discussed by many of researchers.
So, thank you very much.